Is our speaker Benjamin Chung here? Okay, we'll wait for him, I suppose. If he doesn't show up, you guys can go to the other room in the cathedral or any other meeting until the next talk. Yep. Systems by showing a state machine. If Ben is not here, then call Ben. Then Ben arrives, then the talk starts. Yes. It's just a demonstration.
All right. So here we have Benjamin Chung, who is a modeling and simulation consultant at Julia Hub. And previously, he was a postdoc at the University of Washington. And his talk is going to be about synchronous systems and modeling toolkit. So let's welcome our speaker.
Awesome, thank you very much, and I apologize for the delay on this. I'll try to be quick to stay on time. So yes, I'll be talking about synchronous systems and modeling toolkit, and generally about discrete time modeling and modeling toolkit going forward. So to begin with, I'm going to talk about an example that if you've read our documentation, you've probably seen a lot. It's a simple DC motor. We have a voltage source that's connected through a resistance and inductance to a back EMF, which then spins a shaft and then has a load attached to it. In the simulation, the load starts out at 0, and then we have a step change, and then it causes the load to slow down. Apologies, I'm a little bit out of breath. In continuous time, it would be nice if it span at a consistent speed, and to achieve that, we can attach a simple PID loop to it. You can see here that it starts up, we have a little bit of underdamped behavior, it then stabilizes, we then have the step change in load, and then we see a burble and it stabilizes again. With the new support that I'll be talking about today, we can then add a discrete time controller to it. So instead of the controller updating continuously in continuous time, we can instead have it updated at a certain rate. So here it's running at 100 hertz. And you can see that we're ultimately having the same response, albeit with a slight phase delay. But here the controller is now discretized. But ultimately, seems good so far. But the thing is that getting an actual angular velocity measurement off of the load is kind of unrealistic. There are sensors that can do this, but they're expensive and annoying and don't want to add that. So what if we just had an encoder, right? Frequently you'll have like an encoder, it'll just give you a pulse every time it spins a certain amount. Should be good, right? Like we attach this thing, we differentiate it, seems reasonable. So we can do that, and everything goes to hell. So you can see here that once we add this more realistic encoder, so this is a quadrature encoder, and I'll talk more about what this means in a little bit, we are unable to effectively control the plant. It no longer reaches a steady state. And we're seeing all this noise, and it's just ew. So I'll talk about why this is happening, how we're modeling it in dyad, and sort of how we can use this going forward. So we've talked a bit about this before in the context of MTK sample data. But the idea is, behind both synchronous programming and these discrete events, is that instead of having continuous events that hold for all time, for every point in the real numbers effectively, we instead have these equations that hold only at discrete time. We can also, because we now have these distinct times, much more easily and much more commonly talk about times that are integer times, a certain number of integer times in the past. And that's all represented this way. In some of the new stuff, though, we also have a number of different clocks that we can use to discretize time like this. So there's the periodic clock, like I talked about earlier, which just runs at a fixed rate. But we can also have things like event clocks, where the clock is created by a continuous parameter that's crossing 0 that you can construct in any way. One second. And then there's a whole bunch of other clocks that we both have and are currently working on supporting, like a computed clock where you decide the time in the future that it'll run, or a one-shot clock where you get exactly one update and that's it. But these are the ones I'll be talking about here. We also have the ability to have hybrid systems. So here we have on certain discrete intervals, we say, oh, we see that you've achieved 1. What if you achieved -1? And here that causes the system to sort of oscillate back and forth as the continuous time system tries to track the discrete time output. We can also refer to history. So here I'm implementing a very simple discrete time finite differencer. So this is sort of your first derivative approximator in discrete time. And here I'm able to say that the slope between these 2 points is the difference between the current value and the previous value divided by the amount of time it took for us to get from here to there. So in the model that I showed you earlier, we have 4 clocks actually. There's two signals that are coming off of the encoder. So there's 2 sensors on the encoder that are giving us sort of chopper signals. I'll show you this in a second. That's then they're then being mixed together and decoded to tell us how far the wheel has actually spun. And then on this sort of synthetic clock that's built out of these 2 initial clocks, we're then adding up those steps that we've taken so far, differentiating the added output, and then we're sampling the value in that in the summer and differentiating it on a constant clock, which is then where we do the closed loop control. So this is also both supported in Modeling Toolkit and Dyad. So at a very high level, I won't go into too much detail here. This is the discrete time Dyad model. It just wires up what you saw in the previous slide. The encoder, this is Modeling Toolkit. This shows, again, a little bit more of the zero crossing clock semantics. What we do is we just create a zero crossing, which is effectively just a Modeling Toolkit callback, and then that's used to sort of set off equations that occur on that zero crossing. So here, the continuous time events that we're actually observing are created by 2 different sine waves. One of the sine waves is pi over 2 offset from the other sine waves, so we get 2 out of phase. So we have 2 sine waves that are out of phase, and then we're watching the zero crossings. So to illustrate what this looks like, here's a sample of the data from the run. So the yellow curve is, I think, the A channel. The blue curve is the B channel. So the yellow channel here is created by the zero crossings of one sine wave. The blue channel is created by the zero crossings of the other. And then this creates the quadrature signal representing like a physical chopper wheel going past a couple of sensors. Just to show you a little bit more of the synchronous Dyad semantics, here is how we would write an accumulator, which just takes the current value and then which takes the last value and adds the current value to it, and a finite difference, which works the same way as the Modeling Toolkit one that I showed you earlier. The decoder is a little bit more interesting because we don't have a single clock that the decoder needs to run on. Instead, the decoder needs to run on the union of 2 clocks. It needs to run on both on both sensor signals that we're getting to create the decoded encoder output. So what we do is we take the signals that are coming from each of the sensors, we then merge them together, so this creates sort of the OR clock of both of the inputs, and then we resample them using the last value mechanism here onto the union of the 2 clocks, which we then send into a state machine-like decoder that then figures out whether the wheel has stepped forward 1 step, stepped back 1 step, or hasn't moved on this particular clock. So again, as sort of an example of this, what we then end up with is that it takes in this sequence of events where we get the chopper signal coming in, and then it turns this into a 1, a 0, or a -1 that happens on the clock of the 2 encoder inputs. So here, the value is all 1, which is why I've plotted it using points instead of lines. The line plot version of this wouldn't be very interesting. But here, the simple presence or absence of a point is what's interesting. The times that they're happening at is really what's encoding the information effectively about how fast the wheel is spinning. Then stepping through the model a little bit more, we have the accumulator. So now we're adding up these events over time. And you can see that as the wheel spins fast, as we get these points closer together, the wheel spins faster, and as they get farther apart, the wheel spins slower. And as a consequence of this, the summed result, the encoder steps that we've added up, is a slightly lagging discrete time approximation of the real rotation of the wheel, as you'd expect from an encoder. It's doing what it says it does. But where we start seeing the problems is when we go and finite difference it using the block that I showed earlier. In yellow is the real angular velocity of the wheel, and then the blue is the discrete time velocity estimate that we're forming by finite differencing the inputs. And you can see here where all that noise that the PID controller was producing is coming from. Because what the PID controller is being told is, wait, you're going this fast now. No, we're going this fast. No, you're going this fast. Even when the actual speed of the wheel isn't changing that much. So Why is this so noisy? It becomes much more obvious when I take this out of an angular space measurement and put it instead into the raw counts that the differentiator is dealing with. So in the angular space, we're looking at values of like 0.9, but this is actually coming out of us having turned 6 steps, essentially, or 7 steps, or 5 steps. And the difference between 5 and 6 and 7 is pretty substantial in relative terms, and that's what's creating this. Since the encoder wheel can't resolve steps in between them, we're sort of getting like 5, 5, 5, 6, 5, 5, 5, 6, because the true value is actually sort of, there's this sort of residual that's adding up over time, and that's being shown off by this multi-clock discrete time model. So as a consequence of looking at this model, there's a number of ways that we could use to fix this problem. One very common solution that you see in real motor control, for example, is to use a more sophisticated filter to estimate the velocity of the wheel. So you could use a phase-locked loop, for example. We could target a faster set point. 1 radian per second is not actually all that fast. Or similarly, if this is a gear motor, we could attach the encoder to a different part of the mechanism that's spinning at a higher speed. We could use an encoder of a higher CPR. This was a 4,000 CPR encoder. You could use a 32,000 CPR encoder. Or you could, as I mentioned earlier, you could use a resolver that returns a true velocity signal from this. So in terms of how we implemented this, what we do is we take like a dyad or a modeling or a compiled modeling toolkit model, and then we split this up. We split this up into a continuous time part and a discrete time part by running clock inference on that resulting system. The continuous time part goes off and does its normal thing. We don't modify that path. In the discrete time part, what we do is we take the equations that are on the discrete time partitions, we then convert them into heptagon code. I'll explain what this is in a little bit. And then we pass this off to the hep-C compiler. The hep-C compiler takes that heptagon code, mangles it into C output, and compiles it into C. We then compile that C code into an executable binary, which then gets linked into the rest of the modeling toolkit model and is used to simulate the system going forward. So to talk about heptagon a little bit, heptagon is a compiler for synchronous programming languages originally developed at INRIA. What it does is that it takes these equations on clocks that we're producing and turns it into imperative code by causalizing it. It does a bunch of other checks, but we statically guarantee that you won't actually run into these, at least if I did my job right. Importantly, we actually also support FFI down into this lower level, and this allows you to do sort of low-level mangling of clock signals and data that's running on them. In the longer run, we aim to replace this with a more pure Julia solution, but this gets us going. This is a nice way for us to deal with these multi-clock systems. So as a quick little example of what this compilation process looks like, we take a modeling toolkit or dyad model. Here it's a very simple delay element. We then compile it down into heptagon or Lustra-like code, and then that gets compiled into C code. This is obviously a very small snippet. So in conclusion, we now support hybrid multi-clock systems through modeling toolkit and sync toolkit. It's ultimately based on synchronous programming semantics, although I didn't talk about that in too much detail, and with the goal of replacing Julia Sim compiler as the discrete time backend for modeling toolkit. It's currently based on heptagon, like I mentioned, but we're looking at synchronous extensions to Julia in the longer future. We want to have a number of additional semantic features like state machines, structs, and arrays, and fully integrating them into the rest of the discrete time semantics. And ultimately, we hope to release Sync Toolkit in the near future. I say a few months here, but it's probably going to be faster than that. Okay, thank you very much.
All right, we probably have time for a question till the next speaker sets up.
Anyone? Okay.
If not, let's thank Ben once more.
Oh, you had a question?
Please.
Did the semantics that we're using here support what would happen if 2 events happen at the same time?
Yes, they do.
Okay.
So we actually do see that a little bit with the encoder output, and that what'll happen here is that we will like compute the union of them, and you'll only get one event out if both of these were to happen at the same time.
All right, let's thank Ben once more. All right. Our next talk is by Yuri Nuzhdin, who's a software architect at ASML. And he's going to be talking about functionfusion.jl, the algorithm composition framework.
Yes. All right. Yeah, so thanks for introduction. I'm Yuri, and I was, through my career, was working on brain-computer interfaces first for quite a while, where you analyze electric signals of your brain, and then I'm working in ASML, in machine control. But basically, through whole my career, I was fighting the two-language problem, where you implement something offline first in one language, and then you want to run it fast, and that you implement it in another language, they diverge, and this doesn't really work, and you debug this for a very long time. So, So you know the idea that when JuliaCon, that's kind of the solution for the problem, but it's not completely true, because there's some fundamental reasons why this was done before, besides the knowledge of language, right? Because in essence, offline analysis and runtime is slightly different tasks, which correlate a lot. So to address these problems, I'll prototype in this function fusion framework, which I will talk about today. But let's do some step back, and let's just talk about like simple example. Okay, let's imagine that we're making some boat control. That's not really, there would be no model, but you start with some simple model. You say, okay, this works. You have just a couple of inputs. You do something, that's your control. You send the real hardware to the water. Well, it doesn't work. You forget about a lot of things. Let's add more things, right? Your code starts growing. It becomes more complicated. At a certain moment, you say, okay, we need to make it now structurized, right? It's not a single function anymore. It's many functions. We test them, we run them, and yeah, this is keep evolving and getting more complex. So what do we do afterwards, right? We say, okay, now we need more layers. We need even more inputs. We need something that we can pre-compute before, right? You know, the model develops, it grows, and at a certain moment we even say, okay, this doesn't fit the time and budgets anymore, so we need to split it actually, right? And the typical technique there is you pre-compile something up front, or like pre-compute something, and then you run it on a real machine. And of course, when you do this kind of simulation in offline and in online, this is now becomes a really big problem, because, well, if they implement it with different languages, it's even larger problem. But even if it's one language, it's still very different environments. Where do you want to analyze it, right? Probably during your analysis, you want to play with both things as a one item. And in a runtime, obviously, you run the only online part very frequently. So what does it mean? Yeah, there's a differences between that. And this is the typical evolution of the language. And, well, quite often the straightforward approach is like, okay, we start duplicating our code. We start making the code which looks almost identical, but not really. Can we deal something with that? So let's go back. Let's take a smaller model, right? Let's, this is the diagram that you typically will make to explain it to your colleagues. But let's a little bit formalize it, right? Let's add the intermediate data steps here. Okay, now it looks like, okay, the green looks like a data, the orange like a computation, right? I name it differently. I say, okay, the green one is an artifact. And artifact, it's not just a data, it's also a meaning. So when you name it, you don't name it, well, it's a mass. You name it, it's a mass of my boat. And if you have an anchor, well, it's a mass of my anchor, right? Same for computations. Computations, I name it providers, because they provide you those kind of artifacts. They may take some inputs. They also may take no inputs. Maybe they just can read the value from the hardware, for example, from the sensor. And for further discussion for the next 10 minutes, let's assume the providers are pure functions, so you can easily test them. That's very nice, and they have no side effects. This is very nice, because then you can say, okay, I have several providers which take some input, gives me some output, which means, okay, now I can connect them together, right, to get something meaningful out of it. I can construct an algorithm out of it. And this connection can't happen automatically, because if your system already knows, well, in which terms you talk to describe your model, your domain knowledge, okay, this is the inputs, this is the outputs, just connect inputs to the outputs, right? It's very straightforward. So now talk about the package itself, function fusion. It does exactly that in a nutshell, right? You can define artifacts, that's the syntax for it. It will be a lot of macros, sorry for that, but it's in general just generates code for you, which does the job. So you can generate artifacts, and then you can construct algorithm out of it. It will automatically inline the providers inside, and and you will have your algorithm. It will work, but most nice thing of it, you actually have zero overhead of this, right? So now you have ability to declare in a declarative way to connect items in your system, and you don't pay anything for it. And when I say like there is zero overhead for this, it's literally zero. I have unit tests inside which checks that the assembly generated from the handwritten implementation is exactly the same as the one generated by the system. So this is kind of proven work. What else can we do? Well, the first thing, I'm drawing these diagrams, but it actually can generate diagrams for you. It can explain you what kind of system you are building. It can give you an overview of all possibilities of your system. You just specify all the providers, and it can show you what kind of algorithms you can build out of it. It doesn't do any validation. Or it can also take your actual algorithm and show, okay, this is actually what we deployed on a system, right? Maybe we made a mistake, maybe not. Maybe we just keep it for documentation purposes, right, or explanation. And of course, the providers is in essence, it's just the functions, right? It's just the functions with some metadata attached to it, so all this machinery can happen. What kind of providers else can we think about, right? Well, one of the simplest one. What if we have two artifacts which actually share the same data type, right? We can just say, okay, it's like domain name is different, but sometimes they mean the same. So, okay, can we just set the equal? Well, equal is named promotion. We just promote one artifact to another. You get it very easily. Well, sometimes you don't promote it automatically, the one to another. You say, okay, there could be conditions, right? This is how we do the branching in this system, right? Suddenly, there's not just a waterfall. It have branches. And this is a conditional artifact. Okay. What else can we do? Well, you probably describe algorithm in terms of certain effects. And sometimes you want to say, okay, this is kind of abstract algorithm, right? Maybe part of the computation I don't know yet. Maybe I actually want to leave it as a template so you can feel part of your computation. Maybe it's something like, I don't know, something landing on the moon and something landing on the Earth, and I need a source to compute the gravitational effects. They are different. Okay, maybe I don't put it as a constant. I put it as a provider, which give me the result. So we can have the unimplemented providers. And of course, you cannot generate algorithm with something unimplemented because, well, what do you want to compute? You don't know what to compute. If you know what to compute, you substitute it. You just replace one with the other. And the beauty of substitution is it's not necessary to have only unimplemented. You can actually take your existing algorithm and say, okay, here I'm computing the wind effect. This is my new model. I have a stronger model for wind. I just replace one with another. And it will generate still same control system, but with different actuation on it, which is really nice. What else? Yes, this is the example of this kind of substitution. Grouping, it's a very trivial thing. You probably want to group them together to exchange them, right? Maybe you're trying to build hierarchical models. We'll see later how it's going. But the difference between here, what I want to show is actually, okay, you can group them. It's a group. The difference between algorithm and a group in this idea is that algorithm just shows outputs and inputs, right? you can isolate it, right? It's a namespace. The group is not really a namespace, it's just aggregation of them, and you can access the sub-elements from the group, but you cannot access the sub-elements from the algorithm. In this example, well, for example, A2 is not available from the algorithm as an output, and it's available from the group because it's just a group. Sometimes we still want to say, okay, we have this nice algorithm, but we want intermediate data. For diagnostics, for example, right? It's a quite common topic that, okay, if something doesn't work on my machine, I want to just diagnose what happened, right? Well, usually we say, okay, this goes with the overhead. Obviously, you need to save the data, you need to extract the data, but it also usually comes with the overhead. Oh, we need suddenly to rewrite our code because we need to have an alternative solution which works slower because of the overheads, and then we have the production solution which works faster. How do we make sure that they are the same? Well, in this approach, it's very easy. You just say, take the production solution, open it up, remove the abstraction, take the samples that you need, and that's it. Right? It's guaranteed to be that if you change your production solution, it's guaranteed that the diagnostic approach would be updated, that the diagnostic algorithm would be working still in the same way as you intended. All this machinery sits actually on top of Julia, right? I'm using Julia a lot there. It's not really a compiler. It's kind of sophisticated code generator, and we leave all optimization for Julia, and apparently Julia can do this really, really well. The only thing I have to really invent is this context where basically Julia will understand that those variables, they have certain lifetimes, but it's like static call graph friendly, by the way, and all this stuff. On this slide, you can see, okay, you can define the context. It's actually automatically defined for every group, for every algorithm, and so on. You can create it by the default. It's empty, right? Then you can call algorithm, changing this context. By the way, this is again an example that you can produce multiple different implementations of the same algorithm, which have slightly different performance behavior or like external behavior, but they still implement the same algorithm, right? So in this case, it's an algorithm ban, meaning mutating, and you give extra argument, you give the context, and then in the context you get everything which was computed, captured, and here you can see that, okay, we have actually input captured, we have result captured, and you can also see that, well, if you don't ask for the certain things, you don't pay for it, right? All other artifacts are enumerated, that they can happen in principle, but they will not happen. We can even go further and we say, okay, let's eliminate everything which is not computed, so even in the context level we'll not see it, but sometimes it's kind of not very handy. So there's just different flavors that you can opt in or opt out. And of course we talk about the algorithms, but we build algorithms out of algorithms. And there is a possibility for that as well. You can say, okay, this is my algorithm, and this is how I provide the inputs, and this is how I interpret the outputs out of it, right? So if you have something which do Fourier transformation, maybe it's an algorithm which do the Fourier transformation or whatever the transformation that you think about, and then it's applied for data point A, data point B, data point C. You can even, like in this example, I showed that you can even nest the same operation one after each other, so you can build some recursive functions with a controlled depth of recursion. There is no cycles in this approach so far, just because I don't see a need at this moment with the things that I implement with it. But yeah, if you need a certain level of recursion, limited, you can just implement it. So far, it's this is what you already have in the package. And a little bit more, I will talk about it now, but there is one important concept which I want to come back and really go deep on it, is assumption that the algorithms are immutable. Because all this possible so far is on assumption that, sorry, immutable, I said immutable, pure functions, right? You can construct this easily if they are pure functions. If they are not pure functions, suddenly the order of execution becomes important. And this size, as I mentioned, the main purpose for this is also build flexible but performant. And typically the performance, yeah, you have to mutate something, right? If you update matrix size of 1 gigabyte, making the copy of this matrix for every single step in your computation is not really feasible. So in this example, I show you two possibilities, two possible operations, which makes it unpure, and it makes it extra complicated, right? If we will look at operation 1, yeah, it's obvious. It just updates the data, right? It's important in which point of time we will update the data, but actually operation 2 is also tricky. Well, it doesn't really update the data, it produces the new data. But you know how it works in Julia, because it's a pure Julia code, right? If you update X, well, it will be updated. If you update artifact B in this case, the artifact C will be updated as well, because there is an implicit connection between them. So both of them are tricky, and in order to work with it, this is what I'm working now. First, you need to explain to your system that this is actually happening. And because analyzing this is kind of difficult, I made this audit provider sync macro, which calls your provider. You give an example. So I'm not relying on a static analysis. A static analysis of pure functions exists in Julia, but it's not like 100% reliable. It's very debatable what it can derive or not. And yeah, humans can derive this better. Or you can give it a sample, like in this case, you just give a sample of the input, and it will check what happens with the input. If input was modified, if output have connections to the input, if yes, it will just tell you that's the case. If no, it will tell you, okay, everything is good, this is a pure function. And if it's not a pure function, what can you do? You can actually, like in examples below, you can see, you mark that, well, it's a special syntax, right? It's not Julia, but I think it's kind of speak for itself. You mark that, okay, artifact A could be mutated by this, and artifact B belongs to artifact C, so you know these connections. As soon as you know these connections, you actually can tell the system to optimize for it, right? Now the system is aware, so let's look at the frame on the left, right? We have two computations which mutate the same artifact. Obviously, this will produce a wrong result. So what do we want to say? Okay, we inject the copy. The copy is implicit. You don't have to bother with it. The system will decide to inject the copy itself. And usually it just goes with like, okay, everything except the last one have to be copied, so it's fine. But if you change the problem slightly, right, now you have suddenly conditions, then it becomes important where the copy happens. And because the system already knows so much about your potential flow of execution, it actually can make a strategic copy saying like, well, there's a chance that we don't need to make a copy at all. That could be nice. And of course, on this diagram, you don't see the order of operations because it's data flow, it's not order. But it actually generates operations in such an order that this is ensured that this will work correctly, right? Eventually, if the copy have to happen, it will happen before the data is computed. And on a diagram 3, you can see, well, there's sometimes also the cases where you actually know upfront that even if it's a mutating operation, you don't need to make any copies because it will not interfere with anything. So you just omit the copies completely. This is what I'm working on now. It's not yet in a pull request, but it will be there soon. And this will solve a lot of problems with algorithms which wants to work a little bit faster, or maybe a lot faster. That depends on your algorithm indeed. Next to that, there is also like, yeah, what if we want to apply, what if we want to decide what to do on the fly? Sometimes it's very elaborate to just decide based on the if statements, right? Maybe the conditions are really difficult. So here there is a special option, switch provider, and it takes a vector, and because of some limitations of the current implementation, it takes vector of data type, but actually the data type should contain artifacts, and it should contain one of these 3 artifacts. And then it knows, okay, I will have a vector which contains those artifacts. I will create a vector which will contain those artifacts, but I will not compute them always. I will compute them in a lazy manner, because if somebody doesn't ask me to compute anything, I will just not do this. And this really intertwines with the mutability that I described on the previous slide, that it's another layer of optimization. Well, what if they are lazy evaluated? If we cannot predict upfront that they are lazy evaluated? What does it mean? Well, on this slide, it's very simple, right? But if you think about it, the system can grow. You actually can find out that certain artifacts are computed always. You just have them, and certain things have to be copied or not copied. So all this, the system just knows all of this, and what was before done by software people who are trying to optimize the algorithm to dig this last 5% of performance, the system can do it for you. So you're busy with the more complex stuff, like how to make the algorithm. You don't bother with like, okay, how to avoid copies in my algorithm, because it will just figure out some solution which will work. What else? This is also a very interesting thing. It doesn't came originally, but when I start testing it, in the end was the question, well, are my computations correct? And sometimes you have to test it with data, etc. But sometimes I found that, okay, symbolics is really nice. They can actually capture the description of what you compute. And this have a lot of weird crosstalks about like what symbolics actually can do without this framework completely, right? But it's at least to enable this option, I say, okay, we introduce the templated artifacts. They type-based. So in the end, you just describe, okay, I'm replacing this type with maybe with number for the case of testing and with a float 64 for the case of runtime. So in your testing, you can actually run it. You can validate that symbolic equations that you wanted to have there are correct. That's what you expected. And in the runtime, it's just replaced with the floats and it works, right? And then you kind of sure that what you wanted to implement, like let's say you have a paper and there's only equations, right? There is no computation there. So you make sure that what's written in the paper is in your system, and then you just see how it works. And of course, beside that, there is a larger backlog of other features. As I mentioned, of course, there's a lot of things about this mutability optimization, etc. But visualization also can be fine-tuned and fine-polished. It's just to make it more robust for the end users. At this moment, it tends to generate huge graphs, which sometimes very difficult to understand. Certain things on those graphs quite often are not that important, right? Because you, from your domain knowledge, you kind of understand what does it mean. You want to emphasize on the things that are complex, and you want to hide the trivial things sometimes. So at this moment, there's no such a thing. It just generates the whole computation graph, and if your computation is large, then you'll really need to scroll. So there would be some improvements on that. And the other thing is some kind of interesting idea from this conference. Integrate bumper, because this thing, it can also reason about the scope of variables, right? It actually knows the lifetime of them. So you can say, okay, maybe I will use this knowledge to optimize the allocations. And bumper is already the package which can help you with that. And I think there is a good possibility to make this connection between the algorithm generation and memory allocation approaches. So yeah, but that's still on the roadmap. It's an early stage idea. That concludes my presentation. If you want to check the current implementation, functionfusion.gl on the GitHub, and I'm ready for your questions.
Great talk, thank you. Have you thought about first-class algorithms or algorithms that can modify other algorithms as part of the data flow graph?
No, not at this moment. It's intended to help you to generate the code which you will put on the machine. So at this moment, it's already evaluated. So.
All right, I might have missed this at the beginning, but I'm curious how should I interpret the right-hand side of an algorithm definition where it says like bracket P1, P2, P3? What does that mean?
All right. Let me open something like, which slide? So in principle, okay, I will stop here because it's group.
Yeah,
whatever.
any algorithm
the same.
right-hand side.
In principle, I have a chapter in the documentation which describes all this meta language which I put, and it have a logic. In this case, in the square brackets, you describe the providers which became part of it, right? So in this case,
So it's like the set of providers available to use.
In this case, it's a set
Okay.
of providers. There is a special syntax to describe artifacts. There is a special syntax to, well, maybe you want to just define artifact inline instead of using the artifact marker. You can just say, okay, I want this new entity. I want to name it, and this is the data type. So
Okay. Yeah. All
those
right.
kind of
Thanks. Thanks.
Any other questions from the audience? If not, let's thank our speaker once again for the wonderful talk.
Thank you.
Okay. So now we have Benjamin Chung. He is a modeling and simulation consultant at Julia Hub and a postdoc, previously a postdoc at the University of Washington. And his talk is going to be about interfacing Julia with the Kerbal Space Program. So let's give it up to Ben.
All right, thank you very much. So this talk is going to be about how do we make Julia talk to Kerbal Space Program. So first question is, why do you want to make Julia talk to Kerbal Space Program? To me, it feels obvious, but I felt like this needed to be included. So on one hand, like I like writing controller code and simulation code and analysis code in Julia, right? Like I like doing model predictive control in Julia and not in various DSLs or C#, for example, which is something that would integrate more directly into Kerbal Space Program. So on one hand, I have my controllers. On one hand, I have all of my sort of analysis code. And on the other hand, you have sort of, coming from sort of an aerospace perspective, what I refer to as like a mid-fidelity simulation. Like Kerbal Space Program can surprisingly actually sort of beat or exceed GNC simulators from like the early 90s in terms of fidelity, so long as you ignore how the solar system is completely the wrong size. So it's sort of mid-fidelity, like it has cool physics. In particular, it has fun bending modes because of the Kraken, if you've heard of it. And it has wobbles, as mentioned in Little Green Men. So what more could you want? So essentially the idea here is how do we connect controller code or analysis code, or visualization code for that matter, in Julia to Kerbal Space Program. The architecture of krpc.jl is based on a base mod called krpc, which is a cross-language, multi-platform interface mod for Kerbal Space Program that allows Kerbal Space Program to interface with a wide range of other languages, including Julia. So you can also do C#, C++, an ultra-lightweight C target, and in this case, Julia. So the way that this works at a very high level is that krpc opens up a socket out of Kerbal Space Program that accepts RPCs in a custom protobuf format. And what krpc.jl ultimately does is provide a sort of nice, easy-to-use-ish interface layer that sits on top of this format that lets you call Kerbal Space Program and make it do things. So just as a sort of a protocol diagram, so what the first thing that happens is as you fire up krpc.jl is that Julia launches, you make the connection, it asks Kerbal Space Program, hey, what can you do? Because one of the other fun things with krpc is that it's also mod compatible, so if you add more mods and they have implemented an API, like new RPCs can happen. So you find out sort of at runtime that, oh, there's all this other stuff, like there's robotic parts in this version of Kerbal Space Program that you can find out at runtime. And then from krpc.jl, you can ask it, hey, can you do a thing? Or similarly, and I'll show you this in a little bit, you can ask it, hey, tell me all, like continuously tell me all of the things you know about this property. So as a very simple example of some code that does a thing, so what this will do is it will connect to a local, Kerbal Space Program at localhost. It'll ask, hey, what's the active vessel? And then it'll print out what the position of that rocket is in the Kerbin-centered, Kerbin-fixed coordinate system. Here's a streaming example. So what this one will do is it will continuously tell you what the position is. So this sort of long, fully qualified name thing. What happens internally is that there's a sort of a reference name that's assigned to each RPC, and you're able to either use like a very nice lightweight stub that auto-constructs everything for you, or if you want to treat an RPC as like a first-class object that you can pass around and haul around to other places, you can also construct it very explicitly using this. And because we need to sort of do some mangling, the stream interface where you get told repetitively every frame what the position is, does it like this. As another example, you can also do lower level control over parts. So suppose that we wanted to open every pod bay door on our rocket. This is how we could do it. So what we do here is that for the active instance of the game, we say what's the active vessel, we get all of the cargo bays on it, and then we just loop over all of the cargo bays on the vessel, asking it to please be open. So if you go and look at the krpc documentation, the way that we encode properties with both explicit getter and explicit setter is that the getter gets like capitalized name, and then the setter gets this capitalized name set bang, and then the types are directly translated through. So I just wanted to go through a couple of quick use cases. So I'll be talking about this later today, but I used this to generate representative aerodynamic data out of Kerbal Space Program for a trajectory optimization project that I was working on. So here we see like this reusable launch vehicle type thing, and then the aerodynamic lookup table for including stall characteristics for the various fins as they pitch. So this is sort of the vertical axis here is the drag, and then the horizontal axis here is the lift that it can produce in a specific configuration. I believe that this is with the vehicle tilted 45 degrees, and then it trying to pitch back and forth. How much force can it produce? Let's see if I can do a demo, which is always a little bit scary. Let's see. So does this show up? Yes, it does show up. And let me get my VS Code instance over there. Okay, let me start the, I'm going to be doing this kind of blind, so please apologize. Please accept my apologies. So yeah, so what this is implementing is that this is just implementing a hover PD controller. So what this is doing is that it's tracking a specific altitude. It has a gravity-based feed-forward term that causes it to hover, which is why we don't need an integral term. And you can see that as I pitch the rocket around, it's able to hold the altitude pretty much constant, even as the vehicle comes off of the vertical axis. The altitude that it's trying to catch, let's see if I don't screw this up too much, is 150 meters. And as the vehicle gets more off vertical, it gets worse at tracking it. So yeah, so we're down to 145 meters at very high angles, and then at very low angles we end up with 150 meters. Okay, so let me switch back to my presentation. So in conclusion, I'm still developing this, though very slowly. If you look at the commit history on the GitHub, it's very sparse. There are some various future improvements I'd like to work on. So KRPC lets you do server-side expressions, where you can build expressions and then have them executed on the remote server. I'd like to support that better, so you can build up a term and then have it run remotely. This can dramatically reduce the amount of back and forth you need between the server and then the client in order to do things. Similarly, stub versioning is a big issue. As you add mods, as KRPC itself evolves, I do a lot of KRPC development itself, so obviously I run into a lot of problems with this. It would be nice if the client was smarter about knowing, like, when do I need to get the manifest and when do I need to regenerate stubs and trigger a precompile, essentially. But yeah, flying rockets from Julia is fun. If you want to do it, this is a library that will let you. Thank you very much.
All right, we have time for one or two questions if someone in the audience has any.
How scared is he actually communicating with Julia? I think, what's the overhead there? Sorry.
Yeah.
Where does the overhead come from when you're talking between Kerbal Space Program and Julia?
So there's a big one and a small one. The big one is that this is over UDP. So every time you send a message, there's like a packet needs to be made and sent over like loop back and then received. And okay, that's individually pretty fast. But if you're doing 1,000 updates if you're doing 1,000 calls per frame, that really starts to add up. Second one is that the protobuf serialization, which is what underlies this, is not the most efficient. Like, I believe that I think that I'm allocating 2 bytes for every byte roughly. So as a consequence of that, there's more garbage that's produced by this than I'd really like. One nice thing is that through some minor jank, you can actually make Kerbal sort of delay until you get back to it, exploiting the not actually a real rocketness of this thing, and that can really relax your real-time guarantee that you need to maintain. So many performance oopsies can be covered over using that.
Did I get correctly that you basically ask KSP what kind of interfaces it have and generate code on the fly?
Yep, that's right.
Do you have any precompile optimizations for that?
Yes. So the way that this works is a combination of distribution and runtime. in the version of KRPC that's in the registry essentially, I've pre-generated stubs for the typical configuration. So if you just install KRPC from CCAN right now, you'll get those will come in and automatically get precompiled. But those also include the version stub. So if you have a version stub mismatch, it will get mad, and then it will regenerate that code. It will ask you to restart Julia, so that will cause the recompile. And then once you go through that process, you'll have the latest version of the generated stubs.
All right, let's thank Ben for the talk, and the next speaker can get set up. All right, our next speaker is Shreyas Eknathan, and he's a recent high school graduate. And he's going to be talking about adaptive radar methods to solve ordinary differential equations. So let's welcome our speaker. Speaker once.
Yeah, hi everyone. I'm Shreyas. I'm a recent graduate of Lexington High School. Today I'm going to be talking about a project I've been working on in ordinary-diffeq.jl, part of the differential equations interface, namely adaptive order radar methods. And so I'm going to start by giving some background on numerical integration and the problems that we're trying to solve. If you've been to any of the differential equations talks, this will probably be a bit redundant, but I think it's still important to understand what we're trying to do here. So the problem that we're working on are stiff ordinary differential equations, and they're so-called stiff because there is a certain dissonance that exists between two phases of the system. For example, in the Robertson reaction, which I'm sure has been shown at least 3 times at this conference already, we see that this dissonance arises from the fact that the first reaction, A to B, proceeds with a very low rate constant, which means that it proceeds very slowly, while the second reaction, B plus B to C plus B, proceeds very quickly with a very high rate constant. And so when you translate that chemical reaction to a system of differential equations, we find that the first phase resolves very slowly, while the second phase resolves very quickly. And so the numerical integrator has to handle both of these phases while trying to step through the problem. And so now I want to talk more broadly about Runge-Kutta methods as a whole before I get more specifically into radar methods. And so what exactly are they? They're generalized collocation methods to numerically approximate the solution to first-order differential equations, which is a lot of mathematical jargon, but I can explain that more simply through an easy example. So I'm going to assume most of you are familiar with Euler's method from Calc 2, where, for example, if I have a differential equation and an initial condition, I can use my differential equation to get a slope estimate of my function at that point. And using that slope estimate and some small time step, I can then extrapolate a future point along my function. And I can continue this process to extrapolate out my entire curve. And in theory, this is a good idea, but in practice, what we find is that your slope estimate at the start is not a very good slope estimate, and so you quickly diverge from the true solution, as shown on the first graph on the left. And so instead, more robust Runge-Kutta methods will take a variety of slope estimates across your interval from your initial time t to your final time step t plus dt, and using that, it'll create a better slope estimate that you can then use to extrapolate future points along your curve. And so why do we use radar methods to solve stiff differential equations? It inherently comes from their mathematical formulation as an implicit Runge-Kutta method. And so there are 2 classes of Runge-Kutta methods, explicit and implicit. And so the first equation on the screen here shows the explicit Euler's method, so-called explicit, because the future states only rely on past states, while the second one shows implicit Euler's method, so-called implicit, because it relies on an implicit definition of the current state as well as the past state. And we see that because y1 appears on both sides of the equation. And thanks to this implicit definition, we find that radar has good stability properties when trying to numerically integrate stiff ODEs, namely it's astable and L-stable, both of which help it solve these types of problems. And we can see this impact through this graph here from Ernst Heiger, where we see the time it takes for radar, an implicit solver, and Dopri, an explicit solver, to converge on the true solution to the Robertson equation. And we see that radar very quickly finds the true solution, while Dopri, struggling to handle the perturbations of the stiff system, takes far longer to converge. And so now I want to talk more about some of the internals of the radar method that we've built, and I want to start with the most expensive part of the computation, namely this linear system that we have to solve. And so in every time step of a Radow method, we need to evaluate the solution to a costly linear system involving this matrix A inverse. We call it A inverse because it's the inverse of a matrix A found in the tableau, which is just a bunch of constants for the method. And so naturally, a question would be, how can we optimize our solve so that we can make this solution faster? And one way to do that would be to find a rigid structure for A inverse that we can then exploit. And so now we have a goal, namely that we want to find a transformation matrix T that will send A inverse into a nice form that we could use to optimize our solve. And so what can we do better than the naive implementation? We can transform the solver to the complex eigenbasis to simplify the most costly part of computation. And strangely, what this means is that for a real-valued ODE that we're solving in the real plane, we can wander into the complex plane to accelerate computation and come back to the real numbers. And so how exactly does that work? We have to start by looking at A inverse. And so A inverse is a square matrix that has one real eigenvalue and several complex conjugate pairs. For example, here for a 3-stage 5th-order Radow method, we see the matrix A inverse itself along with its eigenvalues and the corresponding eigenvectors. And so one initial idea may be, what if we just take the eigenvectors, make that a matrix, and then try to use that to transform A inverse? And linear algebra tells us that this will give us the diagonalization of A inverse, right? But this is suboptimal because both T and A inverse then have complex numbers in their structure. So instead what we can do is we can take a basis RUV. What that means is I'm going to take the real eigenvector and store that as the first column of T. And then for the complex eigenvectors, which come in complex conjugate pairs, I'm going to separate their real component and their imaginary component, and then store those as the columns of the matrix T. And what this then gives us for A inverse is it gives us a block diagonal structure, namely that for the real eigenvector, we find the real eigenvalue at the top left of the matrix. And for the complex eigenvectors that we've now split, we get a rotation matrix representing the complex eigenvalue that corresponded to that complex eigenvector. And so now, instead of explicitly solving the linear system, we can utilize our structure of A inverse. Because we know this block diagonal structure, we can now decouple our computation into several smaller linear systems since each system along the diagonal is independent. And because of this, we can also parallelize computation because all of these systems are independent. So we've gone from one large system to several smaller systems that are solved in parallel, which thus greatly helps us accelerate computation. And so now I want to talk about some bigger scale heuristics, namely steps, starting with step size adaptivity. And so step size adaptivity is basically the idea of I want to take as big of a time step as possible while still converging, because you want to solve your problem quickly. Right? So how the Radow method will do this is it'll start by proposing a time step, we'll call it h, and then we can get an approximation to the solution at this time t plus h. And we can then use a lower order method to get an error estimate. And so now we can decide, okay, our error is a bit high. We'll now take a smaller time step. Using that smaller time step, we'll get a new error estimate. And then we can say, okay, this error is small, we can accept this step. And so we use lower order methods to adapt the method on the fly. And so we can also blend this with order adaptivity, namely changing the order of the method, how precise the solution is. And so what we need to know here is that higher order methods are more efficient for smaller time steps. So if I'm in a regime where I'm taking small time steps, I want to take a high order 13th order method. And as the time steps get bigger, I will want to drop the order to optimize my solve to 9th order. Even bigger time steps take 5th order method. And so the idea here is that higher order methods are more efficient for small time steps. So by blending order adaptivity and step size adaptivity, we can optimize each individual section of the solve and thus optimize the solve as a whole. And so how do we build on existing work? We have the prior work was from the 1990s in Fortran by a scientist named Ernst Hager, who hard-coded 5th, 9th, and 13th order methods into his implementation. And so to build on this, we have no hard-coded coefficients, as our method can generate all the constants on the fly. It's fully adaptive, stretching 5th, 9th, 13th, even up to 197th order if you really want to have fun. And we also have a modernized Julia implementation with better linear algebra, parallelized computation, and mixed precision capabilities. And so do all these ideas come to fruit when we actually benchmark our method? The answer is a resounding yes. So here I've shown work precision diagrams, which plot time to solve against error. And we find that at the high tolerance regime, where we want very low errors, we perform the best among a variety of other stiff solvers. Other methods will be better for other regimes, but here we are specifically the best. And also I want to point out this graph on the bottom right, which has a comparison against RODAS, a good Rosenbrock method. And here we've benchmarked in the big float regime, showing our mixed precision capabilities, which also further highlights the abilities of our method. And so thank you for listening. And I also want to thank Chris, who's in the audience here, and Oscar for guiding me through this entire project and helping me with all the steps. So thank you.
All right, I don't think we have any more time left for questions for this talk. So we can probably invite the next speaker. So that's Dr. Chris Rakakis. All right, so Chris is going to be presenting a talk on efficient boundary value problems solving in SciML. So let's welcome Chris.
Yeah, thank you very much. I'm presenting, but this work on the boundary value problem solvers, I think that this one has spanned since 2016, actually. For those who know, Yingbo actually started working in SciML as a high school student, and his project that he started working on was the boundary value problem solvers. And now we're hitting 2025, and I think we finally have enough tooling to be able to tell people that we have good boundary value problem solvers, right? And so I want to be able to show people like how cool this algorithm is, because this is probably the one that we spent the most time like putting cool stuff all together in. I'm taking this from Chingyu. This is the student who has been really kind of driving these efforts. So he is supposed to give the talk today, but he couldn't make it here. And also Avik Paul, who's you might know him from Lux.jl and stuff as well. He's also done a lot within the boundary value problem stuff. He's here, and you'll see why, because there's some really cool automatic differentiation in here. So let's dig into it. Why are boundary value problems? Why is this then the topic of our SciML 2025, right? So let's. So what's the background here? Well, the main background is for a long time we've focused a lot on initial value problems, and so if you look at the old blog post that we had back in 2016, I think we kept on updating it to like 2019 or so. Kind of said, oh, here's where we do well, here's where we don't, and one of the places we highlighted is like we're all right, but it's not great. Is boundary value problem solvers, right? One of the other ones was differential algebraic equations. I think we've smacked that down over the last 5 years or so. But boundary value problem solvers was the one where it's just like, okay, we don't really have all the stuff that every ecosystem has, right? With the ODE solvers, we're like, okay, every single other ODE solver, we have a bit-for-bit recreation of it, and then also additions, and we went overboard there. But boundary value problem solvers, we didn't really have much for quite a while. We had some shooting methods, and the shooting methods had some good properties, but boundary value problems weren't our stronghold. Well, what I'm here to tell you today is that we've went overkill on this. So when we talk about boundary value problems, what kind of problems are we looking at? We're looking at the regular boundary value problem. So this is actually something that covers multi-point boundary value problems, right? So basically, it's an ODE where you can put constraints, or the number of constraints. You'll see that the number of constraints, in theory, should be the number of equations that you have. Though it turns out that after you do the numerics with a bunch of additions, you can make there be as many constraints as you want. Also, they don't. If it's a normal boundary value problem, you can put those constraints anywhere. So you can say something like, the maximum of my equation is 5, and it should happen at t equals 5. That's 2 constraints. Boom. That's a boundary value problem. It's probably not the boundary value problem that you've heard of before, right? But usually when we think about a boundary value problem, it's what's the value at the start, what's the value at the end, right? And boom, or what's the value at the end is so that's what you normally call a 2-point boundary value problem. We do have a 2-point boundary value problem constructor, and then we have second order versions of these as well. And I'll show you exactly why in a second, why most software focuses on 2-point boundary value problems and why we no longer care, because that really comes down to tricks with automatic differentiation. So So what are some good examples of boundary value problems? Well, about there are these 2-point PVPs, which a lot of people have written down. So like the swirling flow problem, you find them in satellite motion and all sorts of different cases. You also find boundary value differential algebraic equations, like hydraulic models that tend to have this. But also, one of the things I'll be showing is that things like optimal control problems actually can be represented as a multi-point boundary value problem. And if you just call the boundary value problem solver, it gives you out the optimal control as part of its solution process. I'll show you exactly how that's done, and this is why this boundary value problem solver, we might even rename it to be dynamic optimization.jl, because it does these things that we really wouldn't consider boundary value problems anymore. But this is all about the next steps, right? So what kinds of boundary value problems can we handle? So this is a I thought I had the 30-minute talk though. Yeah. So what kind of boundary value problems can we handle, right? So you can basically split it into two portions, right? One portion are your non-stiff boundary value problems and your stiff boundary value problems. And in the non-stiff section, you have all of your shooting methods, right? And you might go, okay, so first of all, what is a shooting method? And I'll tell you in a second. I mean, basically, you're using an ODE solver as part of the boundary value problem solver. And you go, well, what if if you have stiff ODE solvers, can you use a stiff ODE solver with your shooting method and end up with some? No. It turns out that there are limitations to the stability that you can have when solving these problems, even if you're using an initial value problem solver that is capable of handling stiff equations. And so shooting methods are naturally in this form, for these types of problems, it naturally is less stable than doing other techniques, right? So shooting methods kind of fall into this. If your boundary value problem is easy enough, then you can do some form of shooting. If it's less easy, you can still get away with multiple shooting. If it falls into the hard category, no shooting technique is going to work, right? But then there's also these other techniques like Merck techniques and Merck-N techniques. Merck-N are Nystrom Merck methods, which are non-stiff tableaus that are specialized to boundary value problems. And then we have this whole group of methods that are specific to if you have a very highly stiff boundary value problem and you want to solve that to high accuracy, then there's Lobato tableaus, Asher methods, and Radow tableaus, right? So let me give a little bit of a background on a few of them, right? So what's a shooting technique? Well, the shooting technique, so let's say you have a 2-point boundary value problem, right? So you're given an ODE, and you're given what the value of the solution is at the end. You don't know what the beginning is. Well, maybe I should switch this to the audience that is expecting things to go from left to right, right? Here is the beginning, here is the end, right? You have an ODE that tells you go from here to here, but you know the solution at the end, right? So what you need to find as part of the boundary value problem, the solution is to find the initial condition that makes you get to the right endpoint, right? So it's basically an inverse problem. Find for me the initial condition such that when you solve the ODE, you hit this endpoint. So you can think about it as, well, if I have a way to solve ODEs, I can just use that, right? I pick an initial condition, I solve it, oh, I missed. I'm going to maybe move my initial condition down a little bit, I missed. And boom, oh, this is the right initial condition, right? So that's what a shooting technique is doing, right? It's using the ODE solver and differentiating the ODE solver to basically just find what initial condition will give you the output that satisfies the constraints, right? And this is, if you've done parameter estimation with ODEs, it's using exactly the same infrastructure that you would do for parameter estimation and all those bits, right? Which is why it was one of these pieces that just kind of existed for boundary value problem solvers in SciML because, oh, we worked so much on the initial value problem differentiation stuff, let's just repurpose this for boundary value problems. And it turns out that this is extremely fast as well. In fact, if shooting works, it is by far the fastest way to solve these boundary value problems, right? And you can see that multiple shooting is this kind of technique where you say, instead of going from the start, you go a quarter of the way, and then you have a different solve, go a quarter of the way, and you just split up the interval. It turns out that if you split up the interval, and then you say, oh, there are two constraints. One constraint is that you have to hit the endpoint. The other constraint is that the differences between where you start in the next interval and where you end needs to go to 0. Then you're searching for not just one initial condition, but now the initial condition of every interval. And once you find all those, you have a nice smooth trajectory that goes from start to finish, right? Now I flipped it in the other direction, but we're good, right? So this is the shooting method, right? And it kind of came for free with everything else we did. But as I mentioned, if you get to a stiff enough boundary value problem, these will not be able to fit because the fitting process ends up being unstable. And you can prove that even if you have a stiff ODE solver, this ends up being unstable. And that makes us sad, right? So what do we do? Well, what we do is we say, oh, that's what we have for the first 5 years, and then we say, oh, let's come up with an algorithm that's extremely good. And you go, well, there's no way any ecosystem has the tools to do this until now, right? So what is the algorithm that we're going to do? Well, it's actually built off the algorithms you might have heard before. These are collocation methods, right? So what you do with a collocation method is you write out your method so that way it's, so you take a time step. So let's say we have like Euler's method, right? So we have a time step here, time step here, time step here, time step here, time step here. You write out every single time step. And what you're searching for is what is the value at this time step, this time step, this time step, this time step, all of them, such that your ODE equation, right, your discretization equation is satisfied, right? So the Euler method is un plus 1 equals u sub n plus delta t times f of u sub n, right? You have your simple take the derivative step forward, right? What you want to do is you want to find the values along the entire time series such that the Euler equation is satisfied at every single step and that your boundary condition is satisfied. If you write this out as a gigantic system, you end up with a system where you're searching for what is the value at every single time point. You're searching for what's the value at every single time point. For every time point, you have is my derivative the correct value right at each time point, and you have your conditions. Basically, it just becomes a big optimization problem where you just say solve for what all the values at all time points are simultaneously. So that's a collocation method, right? And you might have even done this if you've used an optimizer before, right? Some people will say use or use jump, or you'll use Pyomo or one of these tools. You'll just write out a fixed time discretization, and then you just say, okay, for this to actually be solving this ODE, then the discretization has to be true at every time point. Run an optimizer and find all the time points, right? So there really isn't nothing new about collocation methods. People do this. So what can we do with these collocation methods that is, making it so that we're evolving in this space, right? So the key here is to do a version of automatic differentiation and specialize the linear algebra so that way you're doing a mixed mode. So part of it's doing forward mode automatic differentiation and part of it's doing reverse mode automatic differentiation with sparsity detection in order to do this adaptivity. So let me explain this a little bit, right? So when you do the collocation method, right, you have all of these different points where you say, okay, un plus 1 equals un You have an equation for what the update step is supposed to be. And you have that equation at every single point in time, right? And in fact, u of 1 is related to u of 2. U of 2 is related to u of 3. U of 3 is related to u of 4 through this time-stepping equation, right? And based off of the tableau that you're choosing, you'll have some kind of banded pattern, right? Because you say, oh, u of 2 is related to u of 1 and u of 3, right? Through the two different equations. And u of 3 is related to u of 2 and u of 4 because of how they're... And so that banded pattern is actually what you're seeing here. So from the equations that you have for the collocation part, you have a banded matrix. But then you also have your constraint equations, right? And from your constraint equations, you have something that can, in theory, depend on any point in time, right? So what happens is, if something like MATLAB or some of the old Fortran software say, well, this is kind of difficult because if in theory, if the constraint equation can depend on any possible value in the time series, then I have a few dense rows in this matrix for the Jacobian. But if I have a 2-point boundary value problem, then my constraints can only depend on the values at the front and in the back. And if that's true, then this density, then everything in the middle here is gone, and I just have some non-sparsity here and here, and I get a banded matrix. Right? So something like BVP4C, BVP5C, Lawrence Champagne noticed this and said, you know what, we will support 2-point boundary value problems inside of MATLAB because you have the structure and therefore everything's a banded matrix and therefore we can specialize how we compute the derivative and we can specialize how we do the linear algebra, right? Great, that's how they did it, but can we do something better, right? So what we can do now, though, is we can say, well, we have the constraint equations, and we have a tool this tool is called automatic sparsity detection, right? With automatic sparsity detection, we can actually look at the function and we can say, do you ever use this value? If we look at a compiler level, we can figure out what pieces of the function you actually use inside of your equation and pull that out to know what the sparsity pattern is. So instead of assuming that this is a dense row, we can actually figure out what that sparsity pattern is. And if it is something that is, then there's two things to do here, right? First of all, if you have a banded matrix, it turns out that you can specialize forward mode automatic differentiation. So if you know things about like forward diff and the chunk size, you can choose the chunk size of forward diff such that it is equal to the band size of the matrix and compute the entire banded matrix here all in one pass through your function. So you build one dual number and then you pass it on through. This is an analytical solution to the coloring problem. See some of my previous, we'll see some of my lectures in the SIMO book about how that analytical solution is done, right? But then this other piece is a row matrix, right? And so while forward mode automatic differentiation is best for doing columns of a Jacobian, reverse mode AD is best for doing rows of a matrix. So it turns out with all that together, the optimal thing to do to be able to compute the Jacobians for the collocation method is do forward mode automatic differentiation with the band size that is determined by the tableau of your method to be able to get all of these terms in blue, and then do passes of reverse mode automatic differentiation to compute these parts of the banded matrix at the top. And that mixture of automatic differentiation collapses and will automatically become Champigne's two-point boundary value problem solution if you actually can discover that the sparsity pattern is banded. So boom. We get that special case for free, but then we also have a very efficient solution for any possible constraints that you write down. And so therefore, we no longer care about it being two-point boundary value problem. Give me whatever constraints you want, and I can handle this efficiently as long as I could do this double automatic differentiation plus sparsity detection. And this is why this algorithm took so long to write. Like, we needed to completely build out everything in the Julia automatic differentiation ecosystem just to make this work. But once you have that, it's a really good algorithm. And then there's I think there's a few other details of the solver process, but that might be, So, and then what we do is then we say, okay, now and so one of the other things that we did here as well, right, is that the matrix that you get out always has this kind of sparsity pattern where you have a bandedness and you have this non-bandedness. It turns out that using sparse matrix solvers from BLOS ends up being pretty slow for this case, and so we have a library which is almost banded matrices.jl, which is a specialized implementation just for these matrix types. That is, I think it was like 4 to 5 times faster than using sweet sparse for these matrices. So so it's a specialized sparse automatic differentiation plus our own linear algebra, and ta-da, that's all you need. That's all you need, right? And so now we got some, and then not only that, but so the reason why Avik was involved in this project is that the first part of this project as well is just to make nonlinear solvers faster for these kind of matrices as well. So nonlinear solve.jl then specializes the internal linear algebra and all the automatic differentiation of the Newton method that's used in the solving process based off of all these properties that I just mentioned, right? You piece all that together, and this is boundary value diffie-Q's collocation methods. Oh, except for one extra thing, we also have adaptivity in the stepping. So after you do one step, it's able to figure out what the error is, the truncation error of the different steps. It will then change all the step sizes and then be able to redo, because you then have a new sparsity pattern to this Jacobian. It will refine the new sparsity pattern based off of the sparsity detection and be able to respecialize the automatic differentiation on the fly as well. So that's all we needed. With all that together, though, then we're able to do something where we're able to say, okay, we can handle any kind of boundary constraints that you want, and we can also do boundary value differential algebraic equations as well, because that's just when you have a differential algebraic equation in the boundary value form, that's just something about the sparsity pattern of this matrix. And so since we can handle a lot of these sparsity pattern pieces automatically, we now the DAs kind of just flow through. Now, one of the things that we also then set up is we made it so that way Modeling Toolkit can generate to this form as well. So you can say, hey, with my ODE system, I also have constraints, right? So your normal ODE, you just define an ODE, give it an initial value, and you let it solve. But now inside a modeling toolkit, you could say, oh, here's my ODE, and here's some constraints that I want you to satisfy. And when you generate a problem with constraints, well, what's a general form of an ODE with constraints? It's this generalized version of a boundary value problem. And so you can call BV problem on that. When you solve it, it will give you an ODE that is guaranteed to satisfy those constraints, or it'll tell you that there's no solution to the ODE that satisfies these constraints. Now, one of the interesting pieces with this, right, that I think, let me see where I am on time. Yeah, so one of the interesting pieces with this, right, so now that we've turned the boundary value problem solve, okay, let me just take one step back here. So we turned the boundary value problem solve to something where you say, write out what the values would be at every single point in time, and write out all the dynamic equations, and write out all of your constraint equations, turn it into one big nonlinear solve problem, and exploit the sparsity, right? But if you turn it into a nonlinear solve problem, you need to make sure that your Jacobian is actually square, right? If you start to say, well, what if the Jacobian isn't square? Well, if the Jacobian isn't square, instead of using a Newton method, you could use something like a Gauss-Newton method, right? You can solve the least squares problem. And if you solve the least squares problem, that lets you handle either as many constraints as you want or as few constraints as you want. But if you're solving the Gauss-Newton version, you really don't care about sizes of anything anymore. So what you could do is you can say, hey, look, I'm going to solve for what the values of the time points are, but I'm also just going to append, just also add to that array of things that you're finding, just add the parameters. And if you do that, you can actually do the parameter estimation of the ODE simultaneously to the solving of the ODE. And it'll fully specialize everything with the forward and reverse mode automatic differentiation and the sparsity all at the same time. And so then you get this nice doohickle, which is, you basically just say, here's my boundary value problem, and my constraint is, so you're given these constraints where you just say, u of pi is equal to 0, u of 0, so this is two ODEs with 3 constraints, and then you want to say at the same time, fit parameters, which means simultaneously to solving this boundary value problem, also tell me the parameters that would be optimal such that these constraints are found. And ta-da, it will just give you a solution that does the parameter estimation and the boundary and the BVP solving at the same time. And again, it's fully adaptive, right? It's adapting its time steps and everything as it goes along to make sure that the truncation error and the error estimates are sufficiently small, hitting the accuracy that you need. Yeah, and so then you go, well, if you could do this with the nonlinear least squares problems, you can also take that internal part where you're doing a least squares problem and just change it to an optimization problem. And you go, yeah, you might as well. If you change it to a nonlinear optimization problem, then you can put constraints in there. Like you can say, oh, there's a maximum value, a minimum value. You can put more equality constraints and inequality constraints. And suddenly you say, okay, now I have a boundary value problem where you're allowed to give me a loss function that you want to optimize, some extra equality constraints that you want, and you also can give me some inequality constraints. And what I'll do is I'll do this exact same process, except now this is that matrix that I was talking about, the collocation matrix and everything, is now the Hessian of the optimization problem that you're solving. But if you send this over to IPOpt, boom, you can do this, and now you get the BVP that is generalized to be able to do any inequality constraints or any piece. When I said at the beginning that we really went overboard with this, I meant it. So now, it's not a 2-point boundary value problem, right? It's a boundary value problem where the constraints don't have to be on the boundary, and they also don't have to be equalities, and you can have algebraic equations as well, and you can have as many or as few constraints as you want. But it's so fast. And then, as I mentioned, there's an error control adaptivity. So what it's doing is that it'll collocate everything in time, so it's choosing some time steps at the start. And what it'll do is it'll use this kind of error control they kind of know from the other tooling, where it'll solve with different methods, it'll take the difference between methods, and it'll estimate what the error is in each of these intervals. And if any interval has too high of a numerical error, it'll split the intervals, right? So then your delta t's will be moving around, it'll be splitting intervals until all of the intervals are sufficiently small. So that way it's guaranteeing that your ODE solution between every set of delta t's is below whatever tolerance you've chosen. So piecing this all together, it'll start with a collocation. It will be solving this with a Newton method or some kind of optimizer to be able to find both the solution and parameters, right? And then if this solution plus parameters is doing something where the numerical error is sufficiently large, then it readapts the time, it splits intervals and such, and it continually does this process until it has found a set of delta t's such that it is solving all the constraints of the equation, inequality and equality constraints, and it is satisfying the differential equation and any other pieces that you've told it that you want it to do. So it listens really well. It's really nice. And so I think at this point, it's probably the most comprehensive and robust boundary value problem solver. It's definitely the only one that I know of that uses both forward and reverse mode automatic differentiation, plus sparsity detection, and has the compiler basically do everything together with it. If you saw my talk on the symbolic numeric methods for nonlinear solving, we plan to be putting that into the middle of this as well, and I'll see what kind of cool code that comes up with. Who knows? But I think that this really kind of demonstrates, one of these things with Julia where, no one could come up with this algorithm in Fortran because you literally couldn't do this algorithm, right? Like you need to be able to read people's code, do the sparsity detection, and so this I think is kind of like one of these like, oh, this is what the SciML organization's really been aiming for years, and we kind of piece it all together in this, and the benchmarks, so we actually, there was someone who then contacted me and said, I have a boundary value problem that's really hard to solve. It was this dehumidifier model. And they contacted me like a year ago and I said, oh, I could help you get this going. So this paper actually recently got published. And inside of this paper, you'll see a lot of benchmarks that show that, that these boundary value problems are about 50 to 100 times faster than those in SciPy and MATLAB. And now the key here, right, is again, the problem that they were solving was a 2-point boundary value problem. So it was one where, they used so Champine had done these specializations and everything. And it's also a large enough problem, so it's large linear algebra is kind of in play. And so even with these factors, you say, oh, we use the same BLAS, we use the same BLAS, and they specialize some pieces in linear algebra. Even with all of that being true, this algorithm is still able to get a massive performance improvement. And so then when you go to all these special cases beyond that, of course, a lot of them don't even support those special cases. Now, there's still a lot more that we're even thinking of doing, right? So the key takeaway is, this is an algorithm that mixes together, automated sparsity detection, automated Jacobian coloring, flexible mixed mode automatic differentiation with parts being forward, parts being reverse mode. It has our own numerical linear algebra implementation, so our own BLAS for these specialized matrices, and then it has a error control adaptivity and extra choices, and it also has symbolic numeric integrations, and then you can also test it against the C and Fortran methods if you want to see. But at this point, it's kind of a beatdown because, again, this is not a very much apples to apples comparison anymore because they don't get to even do automatic differentiation, and we are doing a lot, right? So what are future plans here? You might think like, oh, this project's done. No, the issue with this project is it just keeps on going. It turns out there's a lot you can do with boundary value problem solvers. And the biggest one is you can actually do GPU stuff, right? So of course, like, no Fortran code is gonna, if you give someone a Fortran code and you put it in a BVP solver and it's written in Fortran, like, no one has these things doing GPU because they would require that you get someone to give you a GPU kernel for your ODE. But we could actually compile Julia code to GPU kernel. So let's think about this, right? As we're trying to compute the collocation and the collocation Jacobian, right? We need to evaluate the dynamics function at every single point in time. But it's the same function, just evaluated on an array. So if we could just take your ODE function and without you knowing, just recompile it to your GPU and then parallelize that computation over the GPU. And we do that on the GPU, but the constraints part, right, this other part that we do reverse mode with is not really GPU parallelizable. So we would keep that part on the CPU and we do reverse mode automatic differentiation of those functions on the CPU, while on the GPU we do forward mode automatic differentiation of the collocation methods. So this is in development. We're almost there. And the the benchmarks are going to be great for that. And then we're also making it so that way there's certain other things you can do. So infinite horizon boundary value problem. So you can say the endpoint of my boundary value problem is a parameter as well. Just search for that parameter. Because it's able to change around its delta t, you can make that be a search as well. And also sensitivity analysis of it. So the derivative, actually, I believe this actually works right now, where if you do automatic differentiation of the boundary value problem solve, it will turn into automatic differentiation of the nonlinear solves inside of the boundary value problem solve. And nonlinearsolve.jl does support the Zygote interface, so it should all work out, but we need to make sure that we actually test this well before we start telling people to do this. But yeah, actually, so the boundary value problem stuff goes on forever, but I will say that, you know, one of the things that really happened in Julia with me very early on was in 2016 when we first came out with the shooting methods for boundary value problem solvers. One of the first issues that someone opened up was, does your boundary value problem solver support quaternions? And then someone put a number from quaternions.jl into the BVP solver and said, oh, it works, thank you, and closed the issue. And I looked at it and go, what are people trying to do? And then 10 years later, I'm just like, whatever you guys want to do, we're here for it. So thank you very much, and this project will keep on going. Hopefully we will make it support everything everyone wants. Thank you.
All right, thanks, Chris, for the lovely talk. Do we have any questions from the audience?
Yeah, thank you for the amazing talk. So I think you mentioned that you have to send some stuff over to IPOpt, like Hessians and Jacobians maybe. But what's not obvious to me is IPOpt like really exploiting the exact structures of the Hessians and the Jacobians in the best possible way, or is there still more meat on the bone there?
Yeah, that is a very good question. There is so much meat on this bone. So when we have nonlinear solve, right? When we're doing nonlinear solve, our own Newton methods, our own quasi-Newton methods, our own Gauss-Newton methods, we control everything, and so we can force it to do the right this mixed mode automatic differentiation and our own linear algebra, right? When we send it over to IPOpt, right, we can give IPOpt the Hessian definition, so we can do our own mixed mode automatic differentiation with sparsity detection, yada yada. That part's all fine. But then IPOpt does its own linear algebra, right, because it has its linear algebra built in. So I've always said, like, oh, there's no reason to ever rewrite IPOpt in Julia because it's a pretty good algorithm, yada, yada, yada. But now with this project, we're like, well, if we want to inject our own linear algebra right here, we're going to just need it. So part of what we want to do with optimization.jl now is we want to create our own version of IPOpt that's pure Julia, match its performance and everything, and then we want to be able to do that to then swap in our own linear algebra as this optimization, and that should make the algorithm about 5 times faster. So yeah, right now, though, we have to stick with just that IPOpt slows down that step and uses a sparse matrix solver.
Yeah, and then one follow-up question in the same direction. So you're now working with IPOpt. Maybe it would also be interesting to look at sequential quadratic programming, particularly for the optimal control ones. I think that still might speed things up a lot more.
Yeah, I agree. This was something that I was hoping that we'd get far enough along before Theo graduated, right? So Theo was a student that did a lot of this, you know, quadratic programming and these kind of specialized optimizers in the Julia lab and such, but he ended up graduating before we got this far along on the project. So now I'm going to find the next, basically, I'm mentioning it in a few different JuliaCon talks, like, oh, one of the big things we're going to work on in the near future is optimization.jl a lot, right? That one of the next MIT students I want to have come in will not be doing ODE methods or nonlinear solve methods, but actually nonlinear optimizer methods. I think first project is, you know, do an IPOpt from scratch so that you can get more performance out of that and boundary value problems. And then the other thing is methods for DCP, so being able to take a nonlinear function at the compiler level, prove whether it's convex or whatnot, right? And then these kind of things to be able to, at a compiler level, change things to sequential quadratic problems and all these extra things. So that whole range of optimizers that kind of can integrate symbolic numerics and compiler tricks, I think is a whole 5-year story for somebody. And I think that that's how we'll get that part of the story, because it's already using optimization.jl, so if that piece ever gets into optimization.jl, then it'll just hook together and that algorithm exists. So yeah, I mean, if anyone is out there and wants to if you're joining MIT and you're asking for me what kind of projects are available, I'm probably going to send you this clip, and this is exactly what I'm referring to that is a potential PhD project.
I have a quick question. When doing parameter estimation, how does this scale with the number of parameters?
Yeah, that's a very good question. It scales with the number of parameters in a way that is cubic, right? Because of the LU factorizations involved in it, which is actually the same scaling that you get from an ODE solver that is doing the Gauss adjoint method, right? When you do this with a stiff ODE solver. So is this going to be faster or slower than using the IVP methods? Well, as I mentioned, the shooting methods end up being a lot faster because the nonlinear system that you're solving here ends up just kind of large, right? So whenever the shooting methods end up working, using a shooting method plus an adjoint derivative is just going to be faster, right? But where this is actually kind of interesting, and I have a student that is currently looking into this, is if you do have a parameter estimation problem that's extremely difficult, because of the stability properties of this process, this could actually make it so that way, if it's not fitting using an optimizer, it could actually fit using the boundary value problem solver. And so then one question that you might have is, well, have you tried fitting a neural ODE, where you just put the ODE inside of there, and then the constraints of your boundary value problem is that your line should go through the data points? The answer is yes. It's about 2 to 3 times, well, Avik found one case where it was 10 times faster than the normal way we do it. Another student found that there's a 2 to 3 times slower issue. But then what we're also looking at is, okay, for some of these problems that are really difficult to fit with neural ODEs, such as, for example, some of these highly stiff problems that come from chemical reaction theories and such, right? Can this be something that is stable even when other techniques are unstable? That's something that's still kind of in flux. The first thing that people were looking at was the prediction error method things, and then there's a talk that Helmut gave about what happened with the Neuroblocks crew, and they showed that worked for them, right? So it's like, oh, we didn't have to go to this high-powered piece yet. But I think that there's other cases, specifically with what we're doing with Julia Hub and Dyad, in terms of some of these very difficult systems, for which this might be the method that is best for parameter estimation, but that's still an unproven claim, right? There needs to be some benchmarks on that. I will say one piece about the collocation method. So with the collocation method, because you do everything at all time points at once, it's the everything everywhere all at once kind of approach, the issue is you cannot step to a discontinuity and handle it. So you cannot handle callbacks in this form, and you cannot handle events, and that is one major downside for some applications. So I think that for parameter estimation, this will be a lot better for a lot of these very stiff cases and differential algebraic equations, but it will not handle in the cases with events, which I think is the one downside that I think is inherent to the method.
All right, I think, okay.
Yeah, give Eric a shot.
Very impressive work. Sometimes we do the same problem over and over again, and I'm wondering, is there significant overhead under some scenarios, and is there a way to kind of say, remember this structure so you don't have to recompute quite as much when you do the same problem 100,000 times?
Oh, good point. Well, so the interesting thing about this, okay, so let me show, let me do. So, okay, one of the things with these constraints, right, is you say, okay, let's say, I have a constraint where I say x at the point pi over 4 is equal to, pi minus pi over 2, right? When you have that constraint, what ends up happening is, the sparsity pattern of the green part is, the sparsity pattern of your constraint function is dependent on, where in the time stepping pi over 4 tends to be, right? So, is it between the second and third time step? Is it between the fourth and fifth time step? This is where the sparsity detection comes from, right? It's like, tell me for the given time stepping setup what the sparsity pattern of this matrix is, and it's dependent on what your current choices of delta t are. So if you make those constant, then you have a constant sparsity pattern, right? But then when you do time stepping adaptivity, right, you might add more points before that, in which case in the array, what used to be like, this is computed by a linear interpolation between the fourth and the fifth time point, now might be a linear interpolation between the eighth and the ninth time point, right? In which case the sparsity pattern changes, and then the optimal way to do an automatic differentiation changes. And so it's hard, what we were able to do is we're able to cache one function for the reverse mode automatic differentiation and cache one function for the forward mode automatic differentiation, and then we use what's known as coloring vectors to be able to call it in a way that is specializing on different sparsity patterns. patterns. So it doesn't need to recompile, and it doesn't need to be recompile. It needs, and there really isn't something that you can kind of specialize on there, because every single time that you do the different adaptations and such, you're going to get different, sparsity patterns. And then, yeah, if you're using different parameters and whatnot, it might specialize it might adapt the time stepping in different ways. And so it kind of makes it hard to be able to say, oh, reuse this specialized matrix solve, because you're going to get different sparse matrices each time when you do this. And that's kind of built into the inherent method. And it's optimized. I don't think that there is much you can cache on that anyways. But it is something to be aware of that is like highly dynamic in terms of the sparsity patterns.
All right, I think that's all the time we had, but let's thank Chris again for the wonderful talk. And this concludes this track, so please come back to us for the next one after lunch. That will be the astronomy and astrophysics talk.
actually just reboot the computer? Yep. With the plug-in?
Which one is that?
You just reboot it and bring the presentation back up. Yep.
It got, sorry? It's gone, or it's gone? Is it removed, or?
I didn't remove it from my page, but I don't see it on the.
Okay, so that must be why we have the extra slot now.
They probably removed it from the program, but didn't think to let us know, and
Yes.
so I didn't like update the kind of has the web page.
Yes.
Okay, well, we have more time.
Yes, okay, that's great. You have extra time.
So let's see, so that was going to be at 2:40 that was going on?
Yeah, I think.
So the question is, do we, I guess.
If we have to keep it the schedule.
Yeah.
We'll keep it the schedule, and if we have I think we have an extra open block that you can take.
Can I go after him?
Yeah, yeah. Or, well, you'll go, I think you'll go, what's the schedule?
I can, if it's, I can do it. Can you type your pin in, please? We got 2 minutes.
Oh, yeah, sorry. I'm distracted, trying to do.
We can at least have an extended question and answer session. You can know if you run 2 minutes over, be rude to someone else.
Yeah, I'm not getting you for some reason.
Okay, you want to switch, I can try to switch to a different computer?
Yeah, let's try that.
Okay. So, what I'll need is can I borrow someone's computer?
Yeah.
Thank you. I'll just share the slides with you on Slack, if that's all right.
Oh, yeah, that's fine.
This is the last Intel they ever produced, and they offered me an M1 or an Intel, and I was like, it's not compiling on M1s right now. I want the Intel.
When was this?
2020. Fall 2020. Yeah. No, all 20, nothing. Nothing worked. Or trying to compile, and I was like, I'm not buying a computer that doesn't compile.
This is just going to be like a slide play.
Yeah.
I'm not sure why I have that position, because I like everything about a cluster.
Yeah.
Right, like I have like strong
Battery life is so strict.
Wow.
Well, I mean, now they're.
Yeah, no, I know.
That should work, right?
You want to like
I'm old.
try it, see if it feels fun?
They're all right now.
Yeah, it has HDMI.
All right.
Welcome. Welcome to the second Astro Julia mini symposium for Julia for astronomy and astrophysics. The first one was online only, so this is our first in-person one. So thanks to everybody for making it. We have several speakers. Starting off will be Paul Tita, who's going to tell us about VLBI for Julia.
Okay, yeah, okay, people can hear me. Yeah, so I'm going to talk a little bit about my experience of building a pretty large VLBI code within Julia that's being used by a moderate number of people and a moderate, I would say moderately within the Event Horizon Telescope collaboration, which I'm a member. So just because I'm going to be giving a lot of opinions here, so I wanted to say a little bit about myself, just so you understand my background. I'm currently a postdoctoral fellow at the Center for Astrophysics at Harvard and Smithsonian. Pipe, Harvard and Smithsonian, sorry. I am a quote-unquote radio astronomer. I put that quote-unquote because it kind of fell into it. My training wasn't in anything related to radio astronomy, and I just kind of slowly drifted into that over my PhD and my postdoc. But my main focus is really on using statistical methods to analyze and calibrate radio data, specifically from the Event Horizon Telescope. My background is in physics and math. My undergrad is in mathematical physics. I have a master's degree in applied mathematics, so I kind of have a weird trajectory in this. And then from 2011 to 2021, my primary programming language was C++. This is old school C++, you know, the style where it's C with classes and inheritance. So all the newfangled stuff I'm not super familiar with, but as part of that, I helped write a 100,000 line C++ code that was using the Event Horizon Telescope. I think a lot because of my frustrations with using C++ as an analysis tool. I started using Julia in 2020. It's a funny story how this happened. My supervisor foolishly left me to my lonesome for 2 weeks, and during those 2 weeks I decided to rewrite a massive part of his code in Julia. And then he came back and was like, what have you been doing? And I showed him, and I think he was both shocked and dismayed / impressed. I don't know. It was kind of a weird mix, but it led to some fun projects. And then I think my current major thing that I've worked on, I started called Comrade. I started working on in 2021. It was really also in the middle of the COVID pandemic, and I was sitting at home. My supervisor wasn't watching me again, and I was really frustrated with the 100,000 line C++ code, so I just was again left to my own devices. So story is, if you want me to do something for you, keep an eye on me, because I won't do it otherwise. Okay, so my talk today is about very long baseline interferometry. That's the style of radio astronomy that I am particularly interested in, so I'm going to try to do a pretty rapid overview of it. But what you can basically think of it as is connecting a bunch of dishes across the planet and turning the entire Earth into a telescope. So by putting dishes across the planet, we're able to make our effective aperture size to be the actual diameter of the Earth itself. So this is how you make the highest resolution images in astronomy, bar none. We're many orders of magnitude more precise than JWST and all that stuff. So the other thing that I think kind of drew me eventually to VLBI is that it's rather unique. It's not like JWST or Hubble or something where you can literally think of it as a giant camera, with fancy stuff in between, but it's a giant camera that point and clicks at the sky. VLBI is entirely different. The telescope is actually formed in software itself. And so what actually happens is you have light coming to you. Each telescope then digitizes it immediately. So we record it, we do 2-bit digitization, and then we have to literally ship the hard drives to a central location. And at the central location, we do effectively a Fourier transform or a cross correlation, so Fourier transform, multiply, and Fourier transform. And this is where the actual telescope is formed. So we don't really form our VLBI instrument until it comes to this step. This is effectively, we do this with specialized supercomputers. There's a small number of these institutes across the planet, and they're quite specialized with. You have to have extremely high read rates because it's petabytes of data, and you need to spool through it extremely fast. Once you get that, though, what actually comes out of the correlator is effectively just noise. The atmosphere and the instrument itself just completely degrades the signal. So then there's this step called calibration, where we try to remove the impact of the atmosphere and stabilize the signals so we can actually add enough together to get enough SNR to make something. That's not the end of it, though. I haven't said anything about imaging, and what that is because one of these VLBI interferometers, they don't actually take a picture on the sky. Each pair of telescopes measures a single Fourier component of the image. And so to actually form an image, we have to have many telescopes, and then we rely on the rotation of the Earth to approximately fill in the Fourier plane in a procedure called aperture synthesis. But once you have that, you then have to figure out how to go from this sparse sampling of Fourier components into your actual image, and this is what VLBI imaging is, the procedure of going from this sparsely sampled, heavily corrupted data into something that's like the image that we would eventually publish. People don't want to just look at Fourier components. I don't think anyone can actually visualize that, and if they can, I want to pay you. But so what that means is that from beginning to the end, VLBI relies heavily on computation and software. Like I said, the telescope's formed through software. Actually calibrating or producing measurable signal from data is through software, and producing an image itself is done through software. And I'm going to mostly focus on these two steps, but correlation is also something we could talk about if people are interested in. So it might come to shock you a little bit that VLBI, even though it depends on software, all of our current VLBI software is really old and was never developed for, I would say, modern compute. The two main frameworks I'm aware of that I think almost everyone in VLBI and honestly almost all of radio astronomy use are APES and CASA. Their core functionality is written in Fortran and C or C++, although I think in modern times there's always Python front ends to everything. But where it really shows its age is I think, in its functionality. So APES is a purely CPU-based analysis package. It's limited in its parallelism, and it was attempted to be made parallelized through a project called APES++. That eventually blew up. It never existed, and it was converted into CASA. So when you say CASA, if you actually look at the source code of CASA, if you look at specific files, it will still say APES++ in it. With all of that said, CASA, while being more parallel friendly, is still CPU only. It also really struggles to analyze data sets. I don't know who here's used CASA, but there's this fun thing where if you have a gigabyte some file, it will make tens of gigabytes of temporary like files on your disk to load everything. So it's maybe not the best use of resources. Additionally, I kid you not, installation of CASA is so difficult that when I went to an ALMA workshop like about a year ago, and people were complaining about the installation, they were like, don't try to install it, it's impossible, just use our Docker image. Just stick with our Docker image, don't do anything else, because if you don't do that, you're not gonna set up the build system correctly. So while it is a widely used package, it is difficult. There's also, this is subjective, but this is my perspective. I think the analysis that is done and the style of analysis that is promoted in CASA and APES is old kind of school and was really developed for a time where your computer had like a kilobyte of RAM and you needed to work around that. So they have this kind of approach to imaging called inverse modeling or clean, where it's kind of voodoo and you have to specify the number of clean components you have. There's literally people on the planet who are called clean artists who are really good at it, and then there's schmucks like me who are quite bad at it. And then there's also this like separate calibration and imaging where you know that there's still residual calibration stuff even after you go through the calibration step. So you'll try to kind of image, or you'll guess an image structure, and then you'll calibrate a little, then you'll guess another image structure, and you'll do this kind of iterative loop. This kind of gets you into trouble pretty quick. So motivated by this, I kind of wanted to set out to try to make a more modern VLBI software. One of the things is compute performance. I think this is going to be pretty important, especially as we go into the future. VLBI generally will produce petabytes of data, and then it goes down to terabytes, and then gigabytes, and then megabytes, but it's still petabytes of data at the beginning. And then you have new arrays coming online, like the NGVLA, the SKA, and then I'm biased, so I'll say the NGHT and BEX as well, to additional instruments that CFA are interested in producing. On top of that, I think VLBI code needs to be pretty modular. The reason I say this is that VLBI often these instruments are not built from the outset to work together. It's literally just taking a bunch of radio dishes and talking to your friend and being like, hey, can we use your dish? And they're like, yeah, sure. But the benefit of this is that you don't have to like put $1 trillion or something to build a big instrument. The downside is that telescope A and telescope B might have completely different backends or completely different frequency setups, and you have to deal with this. So having a piece of code that can handle all of these weird corner cases is pretty important. And then finally, we're astronomers, we're not computer scientists. It has to be easy to use by astronomers. I think this is a pretty important piece, especially in the age of Python where everything is supposed to be like really easy. So I don't really want to make a black box like Rust style code or C++ monolith that's incredibly hard for people to use. So my case study, because I am biased, was to look at this with the Event Horizon Telescope. The Event Horizon Telescope is this kind of global collaboration. We have several telescopes across the planet. All of that said, it's most well known for, it's the first ever instrument that was able to take a picture of the horizon of a black hole, and a demonstration that black holes of 1,000 times different size look about roughly the same. So what you see here on the left is a picture of M87. This is the first black hole we ever took a picture of. The one in the middle is a polarized version of it, so light is polarized. That's one of the big things that I'm interested in. And it effectively tells you the orientation of the magnetic field around the black hole, which is quite interesting for a number of reasons. And then the one on the right is Sagittarius A star. This is the black hole at the center of our galaxy. I'll also say this used Julia quite extensively in a lot of its results. A lot of the data analysis used Julia for this, and a lot of the modeling used Julia for this as well. So Like I said, one of the other things, one of the other reasons I wanted to look at this is that the EHT is a highly dynamic and heterogeneous instrument. Effectively, every telescope in the array is different. We have things called phased arrays, which are, instead of a single radio dish, they're a bunch of smaller radio dishes all linked together. You can use this to make an extremely sensitive, effective single dish. We also have things where some telescopes are single polarization, some telescopes measure different components of the electric field. This is rather unique, and I think the EHT is one of the only instruments where this actually happens. We also have issues with specific sites. LMT, it's a great dish, it's 50 meters, can't point, points right at the ground every time we want to look at a source. It's a bit of a disaster. I say that in jest, it's a great telescope, don't judge me. The other reason is that the EHT coverage is incredibly sparse. This is not like ALMA, where you can kind of see the sampling in the Fourier domain is really complete on the right. And then there's also another traditional dish used called the VLBA in the middle. The EHT is incredibly sparse. This means finding the image from the data we record is extremely difficult. And so it's kind of like a really interesting test case for some of the tools that I was interested in developing. Could we pick this out? So our solution to this was a package called COMRAD. It is a tortured acronym of composable modeling of radio emission. I apologize for this, but don't let me name things either. The goals of this were to really test Julia's ability to analyze VLBI problems. I also wanted to take it as an excuse to try to modernize some of the VLBI analysis methods. And goal was to remain flexible but interactive. To kind of solve these things, it's a Bayesian VLBI pipeline. I think it's one of the first Bayesian pipelines. It's definitely the only Bayesian pipeline that can do some of the polarization analysis that we do. It also tries to do this imaging and calibration jointly together, the idea being that we can handle data at a much earlier state. So all the kinds of horrible instrumental corruptions, we can solve for that. And then, I think to make it ease of use, I try to be a better researcher and, make tutorials. So for important things, it is fast enough for the EHT. Things that used to take weeks on a cluster now take about an hour on one thread on my little laptop. This also means we could expand it to much bigger arrays. Here's an example simulated reconstruction, what we would get from the NGEHT array, where instead of just seeing this boring little ring, I shouldn't say boring, but seeing this ring, you can see the whole jet come out. And then on top of that, it's also able to handle really high resolution. Here's a simulated reconstruction using the Black Hole Explorer, or BEX instrument, where instead of seeing this fuzzy fire donut, you can actually see a much crisper image with a photon ring and then this kind of like inner shadow. That actual sharp kind of ring you see there is actually a telltale signature of general relativity. So it's something, at least physically, we're really interested in. And then finally, I want to say this work would not have been possible without my collaborators, Billy Moses, who's a professor at UIUC now, and Valentin Shiravi, who I'm sure if people are familiar with Julia or have at least heard of these people or are aware of them. So I can't show too much of this, but effectively, in a month or two, we'll have more results that use Julia aggressively, but I can't show it, so I'm moving on. Additionally, I think one of the things that we really wanted to hammer at here was, instead of just looking at EHT data, it's really EHT data as a case study. We also wanted to look at, I think, a little bit better or traditional VLBI arrays. So here's an example of VLBA reconstructions. Clean is the traditional kind of inverse modeling guessy kind of approach. You can see it looks like these blobs with like some diffuse tail. COMRAD can improve the resolution by a pretty dramatic amount. It's as simple as we demand that you have to have good fits to the data, and this is what you get. The clean images don't actually fit the data. On top of that, because we do the simultaneous imaging and calibration, we're able to dig up polarization signals much more efficiently. So here's an example of a PKS 1424 source. This is interesting because it's a neutrino candidate, and while Clean is unable to detect any significant polarization from a single epoch, by stacking 42 epochs they can. COMRAD, on the other hand, is able to recover the full-blown polarization pattern from a single epoch. It's just because we demand you fit to the data and of our improved calibration, we're able to increase the dynamic range by 1 to 2 orders of magnitude. I think because of this, Comrade's success inspired a whole new EHT Julia organization. It's being led by Kazu Akiyama, who's a research scientist at MIT Haystack, and myself. The goals were to effectively kind of say, okay, Comrade was really successful. This Julia idea seems to be really successful for VLBI astronomy, so let's try to build out the whole thing. I can't do the whole thing by myself, so we have a large number of packages. Some of them are going to be talked about today. VLBI sky regularizers will be talked by Andy, and Randy's done a bunch of really important work with extending Comrade to do multi-frequency synthesis and I think eventually polarized multi-frequency synthesis. So, awesome. Okay, so what has worked well? So I kind of, this is a Julia Astro, so I kind of wanted to go over what the good things and the not so great things that I've experienced so far with Julia. I think the first one is coming from C or C++, ease of prototyping and efficiency has been a pretty much game-changing. While I used to program a lot of this stuff in C and C++ for efficiency reasons, that would take forever. And as a little quip, everyone complains about time to first plot for Julia. As someone who wrote a helped write a templated C++ library and developed it, I had 30-minute compile times whenever I would make a change. So it can always get better, but it was a pretty big difference going from me making a change to a template library and trying to ascertain an error and then waiting for it to recompile. Julia, it'd load it once, it would take maybe 5-10 minutes to get the first thing going, and then I could edit it. So that was a pretty big change for myself. It's a very succinct language. I would say even compared to sometimes Python, we have some Python packages, and I think the last time I checked, Comrade's about an order of magnitude less lines of code than the Python library, and 2 orders of magnitude less lines of code than the C++ library with equivalent or I would say more features. Part of that is I'm a better coder now than I was, but it's still a big thing. Performance as well. So I think this was the thing that really surprised me coming from C++. I know it's a really fast language, but I was able to manage to get my Julia code to be 2 to 5 times faster than an equivalent C++ code. I think part of this is that it's just really easy to do performance optimization within the Julia REPL. It's much easier to set up a profiler and interactively fiddle with things than it is to set up a whole C++ library or effective compile job for that. Also, because of Julia's excellent reverse mode automatic differentiation libraries, I'm a big fan of Enzyme. I was able to effectively improve the performance of the reverse pass or the gradient by 1 to 2 orders of magnitude, and compared to the C++ implementation, and an order of magnitude more than the Python implementation. And the reason I bring up the Python implementation is that they used hand-coded gradients. So even though that they were using hand-coded gradients, we were still an order of magnitude faster just because Enzyme's very, very good. Package management was also great, coming from Python and C++, where Python's package management, I dare say, is awful, and I've had so many issues with students trying to install packages. Moving to Julia was a pretty big change, and then C++ doesn't have package management, so not having to meddle with my build system was kind of useful. Okay, composability, I think everyone knows that. And then I also want to say enzyme automatic differentiation. I don't think this project would have worked without it. So this was a major game changer for us. Part of the reason I think this has been successful too is we've had a large number of students who have been very, very good. The ones highlighted in green are the ones who are going to talk this time, other than Anna, who had to back out, but she also worked pretty extensively making packages. But I'll let the other students kind of talk about what they've done or their experience using Julia, but the fact that we've been successful with onboarding students, especially students who had no prior experience using Julia, I think is, we can always do better there, but at least it's encouraging that students are able to pick up on the code that we've written. So where can Julia improve? I'm also going to highlight some potential discussion topics here. One, improve tooling. The linting and type checking error handling I have struggled with, or I've been told by people that it's a bit of a disaster, especially the errors are sometimes pretty obscure. I think that's gotten better lately, but it's still, sometimes when people see a heavy like parametric type come out in your stack trace, it kind of becomes overwhelming for some people, and they can really struggle to read those. Also, more performance, and I would say easy performance, where I don't have to dive into some low-level stuff. It's not entirely trivial to scale Julia code from one CPU to multiple CPUs with threading. There's some foot guns there related to the overhead, related to the threads macro. You have to, you have to be like a responsible programmer and realize where you should put the threading thing, but it's still, I think some students really want to just be like, thread it, and it just gets faster, which is really, really hard, but it's still not there. Then I would also say scaling from a single GPU to multiple GPUs to clusters, while it is possible and it's definitely easier than C or C++, it's still sometimes harder. And the reason this comes up is that people come to me with JAX and they're like, I just run it on this cluster and it's no big deal. I think related to that is fusing of kernels would be nice. When you're running on the GPU, being able to automatically fuse kernel calls would be very, very useful. Also broadcasting, I have to talk with Billy about this, but it struggles sometimes with Enzyme for reasons, I think having to do with aliasing, but it still struggles sometimes. And then, yeah, PyTorch JAX, that inevitable thing. Okay, one thing, adoption. Adoption has been, I've been really successful with the students that I've had, but it's because I come to the students and I'm like, you're using Julia, you don't have a choice. Which is an approach, but it's usually because they want to work with me and I'm like, well, unfortunately, if you're working with me, you have to use Julia. I think it's been successful, but it's still the older scientists, some of my colleagues are resistant to using Julia, so improving adoption would be nice. I would say related to this, we have struggled recently to get funding from NSF and NASA, and I think money goes to Python a lot. Finally, organization, I think we're doing better with that. I know there's been a lot of work on the Julia Astro system lately that's great, but I think it's still, we kind of like struggle with the organization, figuring out which package to use, especially there's sometimes a lot of packages that do the same thing, and knowing which one to pick is hard. And then features are missing. I also think this kind of goes to money. So I want to end that with, Julia is fantastic. It's been super beneficial for me. I also want to highlight that I think right now we're pretty poised to like change how radio astronomy software is done. There's a large amount of development that's being done for next generation software from the NGVLA and then two instruments I am aware of, like because I work for them, the NGHT and BEX. They're both looking to change their software backend. So there's a massive opening for us that if we can get our foot door in a little bit, they could potentially have to use Julia for part of their pipeline, which if we have a big organization behind us could be pretty darn important for encouraging Julia Astro going forward. All right, thank you.
Questions for Paul?
Yeah. So have you actually compared clean with your visibility fitting, is what you're basically doing, right?
Yeah, we're doing.
I mean, in terms of sensitivity, do you find a sensitivity improvement? I do.
Sorry, a sensitivity
improvement in the VO
of
not doing clean.
We're definitely way more sensitive than clean. We fit into the thermal noise pretty easily. The biggest thing, honestly, is I find clean's dynamic range and sensitivity is pretty bad. One is the imaging algorithm. One, their calibration is quite poor. I often have to improve the self-calibration that they give me pretty substantially, and that pretty dramatically improves the dynamic range. You don't see so many artifacts.
You mentioned some standard packages like Enzyme, but I'm wondering if you are hand-rolling your own Bayesian frameworks or are using some of the community ones?
I hand-rolled.
Okay.
Like there's pieces of it that's built upon, right? But I had originally tried to use something like Turing. It was just too slow. It was just like I kind of have to have things be pretty performant, and I just found that a lot of the packages, like the surface packages or the really easy to use packages like Turing, were just too slow for me. Too much overhead.
Okay.
Do you have a sense of what it is about your version that makes them more performant?
So I think Turing has to do a bunch of really important things like tracking variables, tracking dependencies, that when they do this, it just complicates the compute quite a bit, versus mine is much more just like, you know, there's a likelihood function, there's a prior, and there's some transformation pieces. So it's, I would say like my interface is more similar to Stan, so it's simpler than like a full-blown Turing thing where they also will, they can do more things than me, right? Like they can easily perform like posterior predictive things. We can do that and all that stuff. It's just, there's overhead in Turing, or at least there was a few years ago when I first started writing this.
So, continuing on this thread, I mean, I always worry with these reconstructions, especially with that level of sparsity, about multimodality. Do you want to give some comments on how well you think you handle multimodality in the imaging synthesis?
It depends. Okay, so, you know, when you're fitting a like 100-dimensional posterior, we have tools. One of them is called Pigeons, which is a parallel tempering package that I helped write with some statisticians at UBC. My experience with that package is that for 100 dimensions or so, we can hit all modes, and we're fine. For really high-dimensional imaging problems where you're talking about like millions of parameters, I'm unaware of anything anywhere that can pull that off for a generic posterior. That being said, I very rarely see evidence of multimodality on those very big problems. At least, you know, you can run the problem multiple times and you always get the same result. That doesn't guarantee it's not multimodal, but there's no way for me to remove it. There's no way for me to know exactly. And you know, to be honest, the bigger thing that I have to worry about is that the VLBI posterior is degenerate, so it would be in statistics sense non-identifiable. There's things in it that are incredibly annoying to have to deal with. One is that VLBI can't actually constrain absolute flux of a source because it's perfectly degenerate with the gains on every telescope. It also can't constrain absolute image position. And then, so the whole image can shift. So we have to have some way to deal with that. There's also with polarization, you can't, when you have a circular feed array, you can't constrain absolute EVPA, so you have to do a fix for that. So there's a lot of really annoying, you can call them symmetries, you can call them degeneracies, you can call them whatever you want, but these are the biggest things I honestly have to worry about more so than a multimodality kind of solution. But it's a great question.
Let's thank Paula, and we can save more questions for the discussion section. And next up is Paul Barrett.
Paul Barrett, the other Paul.
Okay, my name is Paul Barrett. I'm at George Washington University. I'm going to break up this VLBI talks with something slightly different, something more fundamental to, speak in the microphone, please. So, yeah. So, more fundamental to Julia in astronomy, and that is that's astrometry.jl, okay? We need several fundamental packages to actually do astronomy. Astrometry.jl is one of them. So what's the motivation for astrometry.jl? It's basically, the idea is, I've wanted to do this for a while, is to implement the SOFA or IRFA packages. SOFA stands for Standards of Fundamental Astronomy, put out by the IAU, that they've been doing for the last 30 years or so. There are two basic packages that they put out. One is in C, the other is in Fortran. And the idea is to create a package, a pure Julia package that people can use, which duplicates those astrometric algorithms, okay, to do precession, nutation, et cetera. Time changes, all that type of stuff that's part of the SOFA package. And the idea is to have a high performance package, okay, written purely in Julia so that it's easy to install, and also to minimize the functionality, to keep it simple, okay? SOFA itself has 247 functions, okay? Of course, many of them are dependent type functions, but it's a complicated thing to look at, all right, and to understand initially. And the idea was to simplify this and make it easy for the user. So the current functionality is very basic. It just has in there what I need right now is basically to do precession and nutation type work, and also proper motion. I mainly use this to convert from JD to barycentric Julian time, okay? Basically, I need to convert all my observations to barycentric, particularly the time, to do proper time series analysis. And so that's the major motivation for that right now. The current model, or the functions that I do have, do implement all the models from 1980 to 2000, the A and B versions, the 2006 and 2006F, and 2011 and USNO. The 2006 tends to be the default model that most people use, but you do have an option for all of those. So as part of this, to make sure that the algorithms are correct, I actually rewrote or re-implemented all the SOFA packages. And so there's a sub-package called SOFA, which contains the 247 functions written in Julia. Many of those functions are just single lines. They're just very simple, but the idea was to have a complete implementation. And therefore, the benefit is it's a drop-in replacement to the C-wrapped packages of SOFA and IRFA, okay, that are available. There's sofa.jl and IRFA.jl, but many people are using. Well, you can now use astrometry.sofa and get the same functionality. And so the performance is comparable to them. In fact, I think in arrays it's higher performance because the others are C, and you have to, there's actually the overhead. If you're doing multiple objects, like 1,000 different transformations or something, then you have those C calls you have to deal with. And Julia can can vectorize that. And so the SOFA sub-package is designed to confirm that everything is working properly. So plan improvements. So I have worked recently on improving SOFA mainly by getting the performance up. I've done a lot of optimizations on that. And so it's almost all of it is as faster than the C counterparts. And the other aspect that I did change recently, this hasn't been released yet, is instead of having everything as a float 64 type, I'm now using abstract floats. The benefit there is that you can now use big floats or, what's the other one? Or double floats to actually do your calculation. So you can get 30 significant digits if you need to. That works just out of the box without any problem. And the reason for that, let me just say, is the reason for that I had worked with the master clock and basically in time series analysis. And, in the next 5 to 10 years, there will be optical clocks and nuclear clocks, and they will have precision of 1 part in 10 to the 20, all right? And I think in terms of radio astronomy, we need to be prepared for that, okay? Current clocks are now 1 part in 14, 1 part in 15. This will be several orders of magnitude greater. Astrometry, that needs more development to simplify, but we are working on that, or I'm trying to work on that and add more functionality to that. The big issue right now is time frames and reference frames and working out a much better system for that. We do have that in astronomy, but I think I think we need to do better. So the next version that will come out is 0.3. I hope to release that in the next month or so. That most of those changes will be to the SOFA packages, and finally, they're basically two versions of the SOFA astrometric algorithms. So that's nice that we actually have a Julia version out there. The other thing is this people at the IOU SOFA actually contacted me, so I've given them an abstract, and so on their webpage, this package will be advertised, which I think is a little bit of a help to make sure to let people know that it's out there. For anyone who's thinking about using this, please, if you've got requests or features you want done, please submit them to me or submit PRs or whatever, and so we can move this along, because I think it's very fundamental. It is a fundamental package that we all need to have. And I think it's very important as we move forward because, with these large telescopes like Rubin and Roman, where you've got millions of objects, and you have to possibly do precession on them and that type of stuff, I think Julia will be a big advantage in that respect compared to what we have now. And the last thing I want to note is, to go along with this, is that fitsfiles.jl version 2 is out there. You can now actually read. It's a pure Julia version for reading and writing FITS files. That's available, so you might want to take a look at that, because there have been problems with the CFITS.io building that, and this gets around that. That's all. Thanks.
Questions for Paul?
Hi there, thanks for the talk. So I'm actually an amateur astronomer. I do a lot of imaging just as a hobby. Do you know if people in the amateur astronomy community are using this, or has this been mostly confined to like professional or like, in academic settings?
This package?
Yeah, this package, or like in general with the Julia ecosystem, I've noticed.
Or Julia? I'm not aware of any amateurs using a Julia. I mean, they tend to use standard software that other people have written their packages out there for doing amateur astronomy. They tend to use that, yeah.
I feel like I've seen one or two packages for kind of basic image analysis, but
I've been hoping to do both image processing, but also maybe some like hardware development with Julia. So that's not on mine, but it's also been like I have to learn a lot about hardware development part. So
cool.
So I don't know if this is a feature request or a question about whether it's on your timeline, but I'll say this again. I think this has happened on Slack several times. Barycentric correction for radial velocities do not currently exist in Julia to high enough precision. Is that a planned part of astrometry? I mean, you still need, you need to have support for where the observatories are, but everything else you basically already have, and then it's just implementing things like Shapiro delay and a bunch of other complicated stuff. So I mean, maybe you also have opinions on that. Yeah, and leap seconds.
But we have just discussed this. If you could provide, an algorithm or a flow chart of how that would be done, then yeah, that could probably be done much more easily. So,
Okay, I would be interested in providing that because it's a real bottleneck. I think that it's not yet in Julia.
I mean, one of the big issues that that does need to be done is, the ephemeris, and that needs to be, the really accurate JPL ephemerises need to be added to get accuracies of, 1 second or less in terms of barycentric.
Yeah, I think a bunch of the ephemerises were recently added, actually. There's these separate ephemeris packages for querying the JPL ephemerises.
But SOFA has the default, DEO5 or something like that, ephemeris, and that's what I'm using now, but I don't have all the other ephemerises in there.
I think in the RV community, Bary CorePy is kind of the standard, and I believe it's querying the JPL ephemerises to basically do the hard work for it, and then doing a few things on top of that. So there's a reference, something you can compare to.
Right. Well, there is software. The people who do spacecraft type stuff already have. There is a package that does all of this. We just need to integrate them.
This is actually about FITS files. If fitsfiles.jl doesn't segfault, that's already great compared to cfits.io. But I guess I'm also wondering if you've done any performance comparisons. Is it similarly? Is it roughly the same speed? Is it faster? I feel like that's probably possible. Do you know?
I don't know. I've just been working on the functionality at this point, I mean, FITS is difficult to implement. So, you know, it's to the point where we've got the basic functionality. You can't expect for the world coordinate systems, that's not there, and there's a bunch of other features that need to be added in point 2. But you can basically read in a FITS file. I mean, you know, I can read in CRISM files which use bit vectors and that type of stuff. So, you know, you can actually do data analysis. I do use it for data analysis. But if you want to do more advanced stuff, then you got to roll your own kind of thing. But I think it's, you know, it's probably comparable. I don't see why it wouldn't be. You know, I think you know, if you're reading in binary tables, it's kind of slow. I just haven't optimized that. I'm sure that could be done. The other thing is I read in the entire file at one point in time, and I realize that's a bottleneck, but, you know, I'll change that in the future. That's an optimization, right? I just want to get to the data.
Let's thank Paul again. Next up is Iridani Chavez. On multi-frequency imaging for radio astronomy, interferometry.
Is it good? Can you all see it? Okay. Oh my God, y'all are so tall. I'm 5'1", okay? Okay, hello everyone. I'm Mirandi. I'm a almost 4th year grad student at Harvard. I'm hanging on to that final month, okay? And well, I was going to talk to you about Bayesian multi-frequency imaging for radio astronomy. And then I arrived at JuliaCon and I realized I shouldn't talk about this. I need to talk about this. How do you make Julia more accessible to astronomers like me? Why? Let me just tell you about my experience at JuliaCon so far, and maybe a little bit of my background. I am a trained astronomer. I have never taken a programming class. I have only, my background is just pure astro and physics and, no official programming training. I learned Julia because, as Paul said, if you work with him, you have to learn Julia. So he's been the Julia guy for me. I've had a great time, though. I really like Julia, which is why I'm here. But this has been my experience at this conference. Here's all of you guys who are so cool and so knowledgeable and so expert, and here's me, and I have no idea what the hell's going on. I'm sorry I don't understand most of your talks, because I don't have the background for it. And I think that's actually representative of a large amount of potentially your students and your colleagues and people who are also astronomers and don't have that programming background and just see programming as a tool for the science. I think they would be equally as lost in this conference as I am. And I think catering to those people is actually really important because that's how we get it to proliferate into the community. So let me just tell you how I learned Julia and why I learned Julia. I'm really sorry to say that I mostly learned Julia because I had to. I did think it was cool, but I was kind of forced to. Now I use it because I think I like it more than Python. But that wasn't how it started at first. Also, how I learned Julia, I did use docs and online resources and stuff. Like, Paul Barrett, I definitely saw your AAS tutorial at one point. We're going through the GitHub and stuff. I definitely did that at one point. But it was honestly, mostly just having a Julia guy in my group teach me everything. Thank you, Paul. But then most people do not have a Julia guy in their group. They don't have a Julia person in their group. They don't have someone to be that in-person expertise to really facilitate that learning for them. So how do you get those people to use Julia? So I have a pitch. This is what I wish I had. An online project-based boot camp for Julia in astronomy. This is very heavily inspired by the UPenn Astrophysics Summer School, by the way. I think it should be online to increase accessibility because this room is not full. Even if we had a beginning Julia tutorial right here, right now, let's learn Julia. If we did it online, we could have virtually this whole room filled. We could have many more rooms filled. A lot of people, especially in this funding day and age, are not going to have money to send themselves or their students to an in-person workshop, unfortunately. I think it should also be project-based. I think we should give students or participants a research project to complete, because then they will learn the aspects of Julia that are most relevant for research and also be motivated to learn those aspects, because that's how I learned. I learned because I had to and learned it was cool along the way, but this is really, I think, the critical key. Also, by bootcamp, I'm picturing something, I mean, this is very vague, a mixture of assignments, recorded lectures if necessary, but especially like online office hours so that students or participants who don't have that individualized expert interaction can receive that from these office hours, like that individualized attention to get all of like either what they feel like are just silly questions or really like in-depth technical details, like maybe they found a bug in your package and they didn't realize that, like, but overall have a mix of all these things to just get everyone off the ground with a base level of knowledge to then work off of. And assume that they only know Python and that they don't know anything about programming, because I definitely didn't. So, what are the things that actually taught me, Julia, and how would I actually implement this? So learning for a research project, I basically said this already, gives participants a clearly defined research task that if you were to give them Python, they would know exactly how to do it. The challenge is not the research task, the challenge is doing it in Julia. For online resources, I think these research projects should be designed to naturally introduce new Julia concepts that are different from Python as the project progresses. So start off the beginning of your project with something that maybe the only difference is literally just syntax. And so they learn syntax. But then as the project progresses, you gradually introduce new ideas so that they are able to like learn the aspects of the language that are very different from Python, but also still very useful and helpful in research. And also, I think it should be a very general baseline level of knowledge, but then link and provide resources to more advanced materials and like online resources for those participants who want to go that extra mile, who, you know, they're really picking it up really fast and they can go further. I think it should also like have a way to link to that and also just have a, Paul, you mentioned something like organization of Julia packages. I think having something like this could just be, here's all of the Julia packages that have to do with astronomy. Here they are all in one place, and you can just have that resource for yourself. And I think this part is really, really important, that individualized interaction with knowledgeable experts. People who don't have the Julia guy in their group are gonna really, really struggle learning it because they don't have that resource accessible to themselves, and Stack Overflow is like scary. And I think this could be done with online office hours. So yeah, that's it. This was a leftover from when my talk used to be science, so you can just ignore that. But the question I really want to ask to you all is, how do we make astronomy accessible to the wider astronomy, Julia accessible to the wider astronomy community? I think we need a boot camp, but what are your thoughts? I would love to hear all of your ideas, and thank you for listening.
Thanks, fantastic. Thanks, fantastic talk. I am the guy people learn Julia from in my group at Harvard, also at Harvard, fellow Harvard PhD student. We work in particle physics, and we actually started 3 years ago. We have our own Julia HAP, high energy physics workshop, which is happening next week at Princeton. And then we do exactly this, right? We have students who forced or through classes picked up Julia and wants to use it for their analysis, and then we have like topical meetings, trainings that includes basic Julias and also domain-specific skills and packages and tutorials. So I think that's might be viable if you can find a suitable places and fly people, or they can fly over. So that's a possible route.
Okay, thank you for letting me know. I'll definitely look into that because I think building this off of existing resources would be really great. We shouldn't have to rebuild the wheel.
Hi there. First of all, I wasn't planning to stick around for this talk, but I am so glad I did. Not only for the Big Bird slide, but also because I am an amateur astronomer, and I have been very interested in integrating Julia into my astro imaging workflow, and potentially in the future. I know that there's actually been, like, from the AAVSO, like a call for, like, we need more variable star observations. That's been something that, like, as amateurs, we're actually in a really good position to do. So I think my big, like, thought on this is I would love to see, like, this be accessible to a community of people who may actually be taking their own data every day. Like a couple of weeks ago, I was imaging Messier 24, and I just spotted an asteroid in my images, and I was like, oh, that's its own story that I can tell you about if you're interested. But I do think that there is a very good opportunity to make this accessible to people who are just, you know, at home taking images and might have data that could be very useful that and there have been so many things that people have been missed recently, like the Andromeda oxygen arc, that I think, as amateurs, I would love to be part of that, just by chance. So yeah, thank you.
No, thank you.
All right, I think we should hold more questions for the discussion and other comments on maybe building out the Julia astronomy education ecosystem. Seems like a good talk for the discussion section. So let's thank Ardani again. And next up is Andy Millipore. Yes. Oh, very good. And
Okay. Yes, I'm Andy Millipore, and today I'll be talking about regularized maximum likelihood methods for black hole imaging, sort of building off some of the things that Paul Tita was talking about. Okay. Paul already gave us a really nice overview of very long baseline interferometry, but I just want to recap really briefly how forward modeling approaches to radio interferometry work in the first place. So what we start off with is the image model, which is some estimates of the true sky brightness. And we forward model that, which involves taking the Fourier transform, applying, say, antenna gain corruptions and whatnot. From that, we get simulated observation products. And by comparing that to the true observation products, which are taken from observation, we form some likelihood function, which then informs our image model, and we iterate this over again to ideally optimize our image model to hopefully match the true sky brightness, to match the data. And what Comrade does, which is the package that Paul introduced, is do this in a Bayesian manner. So it forms some posterior from the likelihood function and priors on the image model, and then samples the posterior. But from a regularized maximum likelihood approach, or RML approach, instead we want to form a cost function, which is a data error term plus some regularizers. And these regularizers control for things in the image like smoothness or sparsity. And we can use the negative log likelihood as the data error term. And rather than sampling the posterior, what we want to do is minimize the cost function. And from these two equations, we see that they're really two sides of the same coin. We're just turning the prior function into these regularizers. And so with that in mind, what we've done is implemented RML in Julia as this VLBI sky regularizers.jl. It's really just an extension of Comrade adding regularizers instead of priors. And this QR code here, which will come on later, is a link to the documentation, which is not really yet complete. It has a single tutorial. And specifically what we've done is implemented a bunch of popular spatial regularizers. So this, for example, L1 norm, which regularizes for sparsity, or total variation and total square variation, which control for smoothness. We've also added a preliminary, still being tested, polarization regularizer, this PS distance, or Poincare sphere distance, which controls for smoothness and the polarization angle. And what the user can do in this package is compose regularizers in any linear manner. They can add regularizers or weight them by a scalar. It can also evaluate them in different domains, so either the linear or the log domain, where the log domain is often useful for increasing the dynamic range or the contrast of the image. And what Julia has enabled us to do, and which I'll talk about more later, is that the user can define custom regularizers. They're not limited to just these ones that we've already implemented ourselves. And I don't want to talk much about the package itself or the science behind it, but here's some sample imaging of some real data. So on the left is some published results from the M87 supermassive black hole from the 2018 data, which was just published last year, I believe. And specifically, I've chosen the two other RML packages that EHT collaboration uses, which are EHT imaging on the left, and that's a Python package, and Smiley on the right, which is a Fortran package. And that top row is the sort of raw fiducial results, and the bottom is the same thing but blurred to the nominal EHT spatial resolution. What I have on the right is our results from this Julia package. It ran super quickly. This is just that single tutorial on the GitHub, runs in a couple minutes, and we can see that we get results that agree with the published results, which is nice. Okay, for the last probably half of the talk, I want to talk more about the Julia side of things. And the first question is, why add RML functionality to Comrade in the first place, since Comrade is already a full Bayesian imaging software? And the most basic answer is that RML remains a popular choice for VLBI imaging, particularly within the EHD community. Yet these other packages, in particular EHD imaging in Python and Smiley and Fortran, are not nearly as fast or flexible as we would like. And that is sort of improved upon by this Julia implementation. And there was some discussion maybe back when we were starting this about maybe doing it in JAX or doing our own native Julia implementation without Comrade. But by adding it to Comrade, we're able to piggyback and use the likelihood function from Comrade as this data error term in RML. That just simplifies everything and puts it all together in one nice, larger infrastructure. And we all get all the other advantages of Comrade, such as hybrid modeling. So we can simultaneously fit a geometric model like a ring, a non-parametric image for small-scale flux, and a large-scale Gaussian maybe for the large-scale flux. And that's either complicated or impossible with these other RML packages. And also works well with other simultaneous developments for different Comrade extensions, which are ongoing. As Paul mentioned, there's some work to do stuff in the time domain, and Randy's now changed talk on multi-frequency synthesis as well. And some of the benefits of Julia I faced as a student coming from Python only for the past 6 or 7 years. I really enjoyed the multiple dispatch and type hierarchy, which not only enables easy integration with the rest of the Comrade ecosystem, but also simplifies the implementation of user customizable regularizers. So a user can just define a new sort of subtype of abstract regularizer, and everything sort of meshes well with the multiple dispatch, and just have to define what the function does, and that's all. Another huge thing is auto-differentiation through enzyme. Of course, that's one of the main factors behind Comrade speedup, and that applies to us as well, which makes us much faster than other comparable RML packages. It also eliminates the need for handwritten gradients, as Paul alluded to. These EHD imaging and Smiley use handwritten gradients, which, for example, for EHD imaging can look like this for something as simple as a total variation regularizer. And that's simply just not needed for the Julia implementation. All you have to do is specify AD type equals autoenzyme, and everything just works out. I'll also note here that Comrade previously also implemented Zygote as an AD backend, and we sometimes faced some errors with that when doing custom regularizers, but Enzyme seems to have gotten rid of all those issues, which has been really nice. And then some smaller things. I really like the convenience of Julia compared to Python. For vectorization and broadcasting, for example, you just add a period after your function, even if it's user-defined. There's also been this nice package I've been using, Tulio, which is an Einstein sum macro. And it takes something like this in Python. So the above is the total variation regularizer in Python, which is 15 lines of code, not terribly long, but a little bit cumbersome. And now it's just a single line of Julia code with this Tulio macro. And then just other macros in Julia that allow for really quick benchmarking and profiling that also nicely integrate with VS Code, which I've been enjoying. And then easy parallelization and multi-threading, which is pretty annoying in Python, but has really enabled me to use the full capabilities of my sort of 12-year-old PC. And yeah, so in summary, we've implemented RML methods in Julia as an extension of Comrade, and it's faster and more flexible than any other RML packages that are used by the Event Horizon Telescope, and that's all been enabled by Julia. And just overall, Julia offers many small and large-scale benefits in package development. And again, here's that QR code to the very bare bones documentation that will soon be filled out, hopefully. Thank you.
Questions?
Hi, you said it was implemented as an extension. So is it a separate package that you add, or is it just is it loaded in as a package extension when you load something else?
It's a separate package.
Okay.
So yeah, a little bit complicated, but not too bad with Julia's package manager.
All righty, let's thank Andy again. Next up is Dominique Chang, who's going to tell us about Krang, physics-informed images of black holes.
Is it loaded? Okay, great. Okay, hello everyone. I too was going to do a science talk and realized, oh, that's not correct. So I changed, so now I'm talking about the code that enables the science. I'm going to be talking about my ray tracing code, krang.jl. So what is Krang? Krang stands for Kerr Ray Tracer for Analytic Null Geodesics. So it's kind of different from a lot of existing ray tracers where they kind of allow you to implement whatever metric you want. This is very specified for the Kerr spacetime, and the reason for that is because the Kerr hypothesis seems to be correct, and if you want to fit data, you want your algorithms to be as fast as possible. So there's a lot of speed up that you can benefit from by just assuming the Kerr hypothesis for the black hole. In particular, since I'm a member of the Event Horizon Telescope, and there's specific phenomenological features associated with images of black holes that we care about, particularly sub-images, by essentially encoding a ray tracer that uses analytic algorithms that allows you to more efficiently decompose images into sub-images and so on. I'll go on to and show an example of what I mean by that if you're unfamiliar with the idea of sub-images from around black holes. The other benefit of coding things analytically is that if you use ODE solvers, you get an approximate solution. And if you care about derivatives, then whatever order your approximation is for your solution becomes a lower order for your derivatives. But if you use analytic solutions, you kind of have the exact answers for your derivatives. So there's that additional benefit. Okay, so what does Krang get you? It's GPU compatible. So if you want to ray trace on a GPU, it's got you there, got you covered. It's also is automatic differentiable, mostly through enzyme.jl, partly because that's kind of the easiest one to implement, and also partly because I work a lot with Paul and it interfaces with Comrade a lot. Okay, so why Krang? The main goal is for using it for studies of black holes. So we know that black holes exist. We know there's a lot of evidence for black holes. We see emission from blazars and quasars. We see compact X-ray sources. We see large radio jets, and some other things that people speculate could be black holes. For Krang in particular, the way how it works for ray tracing these images of black holes is that I kind of embody this philosophy, and this philosophy is not really unique to Krang. It's kind of common in a lot of ray tracing codes that exist out there. But the idea is that Krang ray traces what are called meshes. And meshes are just some composite of a geometry and a material. And the idea is that the geometries encode where emission is being emitted, and the material is just local physics. Physics, one of the important concepts of physics is that everything is local. So this decomposition kind of is embodying that philosophy. So in Krang, there are three main geometries that have implemented so far. There's this conical geometry, which I'll show the reason for why that's there later on. There's also this level set geometry, which is kind of a more generalized version of the conical geometry. And then there's this mesh geometry, which is just, you can essentially import a STL file like one would use for 3D printing, and it just drops it in the Kerr spacetime, and you can ray trace that. So that allows you if you have some weird accretion flow around a black hole, you could design something strange in order to model that. The materials in general, just how one defines the local emission physics necessary to render the geometries on the screen. Okay, so what can you do with Krang? So this is just an image showing just some rays that are coming in from these are the rays that lands at some observer that's looking at the black hole at a nearly equatorial view. So let's look at that conical geometry that I mentioned at first. So the conical geometry is a spin axis centered cone with its apex that's placed at the coordinate origin. So this is just showing what happens if you take that cone and open it up around the black hole and then close it out on the other side. This is what it looks like when ray traced. And furthermore, I'm showing you the image of said cone decomposed into sub-images. So whenever you look at the source around a black hole, you get a single image of a source can be decomposed into multiple sub-images. And those sub-images correspond to how many times light has wrapped around the black hole before it reaches you. So at the top, I'm just showing the most direct sub-image. So light did not wrap around the black hole. The middle shows the first indirect subimage, so light wrapped around the black hole once, and then the bottom shows the second indirect subimage. And as you can see, as it wraps around the black hole more and more, it gets thinner and thinner on the screen. Okay, so that's geometry. So let's talk about materials. So implementing materials is very easy in Krang. In general, it's just a functor. It's a functor that needs to be a subtype of abstract material. That's basically it. This is just an example of a material that essentially returns an emission of 1 whenever the ray intersects the geometry. So that's all it is. And if you took, say, that same cone geometry that I showed before and just asked to ray trace the direct image and the first subimage and you were looking down at the cone, like you're looking down through the apex of the cone, then this is the image that's rendered through that. So you get a white band where rays had intersected that geometry twice, and you get an orange band where it intersected once. Okay, and of course you can define other, one of the reasons that this decomposition is helpful is that oftentimes you tend to think about, at least in the EHC, we tend to think about the emission geometry that's very separate from the emission physics. So one could say swap out that X material emission physics and pop in a more physically realistic emission physics. This is just an example of a synchrotron emission model with a power law electron distribution, and as you can, and that exact same image that I showed before gets modified by quite a bit. Once you encode the physics, you actually get something that kind of looks realistic. And this is just showing the said same geometry ray traced with this accretion material to give rise to Stokes signs, Stokes Q and U parameters. This material to implement it has no Stokes V. So I mentioned that's a code geometry. Now the level set geometry. So the idea of a level set geometry is that suppose you want to implement some surface in there, and the surface has a nice mathematical description. If the surface is defined by a level set, then I got you covered. So it's very simple to implement. This is just an example of a paraboloid where essentially, again, it's just a functor, and it just needs to subtype abstract level set geometry. And as you can see, all it just does is return that function. It just returns that function, and wherever that function is 0, it will ray trace that as an intersection. So if you took that same X material from before and ray traced it for that paraboloid around the black hole, this is what it looks like. It looks like a paraboloid, and then you see the photon ring there. That's the first subimage. And again, everything is modular. So that's just the code for the paraboloid. I can just take the same synchrotron emission model that I wrote before for the cone geometry and just apply it to this paraboloid, and once doing that, then you get something that looks even more realistic. So I think that's kind of been hard to model. That is often talked about are jets that have limb brightening here. You can see that if you just say take the synchrotron emission and you kind of get the things right, you can manage to get limb brightening. Yeah. And the last one is the mesh geometry. So I'm just going up in levels of abstraction. So this is just like if you don't have a function, you just kind of, I don't know, you're good at Blender or something. and you can just draw the thing that you want to represent. So this is an example of the Stanford bunny. You can just use geometrybasics.jl to import it. If I drop that bunny in the space-time and just put it in front of behind the black hole and ray trace it, this is the image that you get. And of course, I can drop a synchrotron emission on said bunny, and you get something like this. The electron distribution is kind of flowing. I'm not sure how this is on the. Yeah, it's flowing this way. So the side where it's brightest is just where things are boosted, Doppler boosted towards you. Okay. So now that's just a gist. That's an overview of what's going on. So now for the science cases. So a lot of these science cases. There are additional science cases beyond what I'm going to show here. These are just kind of the science cases that I've used my code in particular to work on. So the first is this Bayesian black hole photogrammetry paper. So just quickly, I'm going to summarize the background. So the EHT produced the first image of the shadow of a black hole from observations made in 2017. The image came out in 2019. Those are the images I showed below. Sorry. And the analysis that was done for these images involved various model fitting techniques. And the models we tend to bucket them into two categories, either geometric modeling or imaging. And the idea of imaging versus geometric modeling is that the imaging models are very flexible, but it's hard to perform inference with them. Whereas the geometric models are quite inflexible, but they have a very precise interpretation. There is, however, a caveat to the geometric models, which is that they are a model of the image on the sky and not a model of the bulk space-time itself. Like, they're not actually a model of the bulk accretion flow. So even if you do geometric modeling, in order to extract information about the system that you're looking at, there's some additional steps that you have to take. So in particular in the EHT, they do various things like an alpha fitting procedure. They try and use the geometric models kind of as a bridge between their expensive general relativistic magnetohydrodynamic simulations and the data that they're observing. The long and short of it is just that the geometric models do not directly give you information about the system that you're looking at. So then there's this idea of photogrammetry. So what I'm implementing is not precisely photogrammetry, but it's in the spirit of photogrammetry. So the idea of photogrammetry is that you have some model for the way that objects kind of, their surfaces appear in space. And then you have multiple images, and then you want to fit the images with your model in order to figure out what the arrangements of those of the facets or the meshes should be, and the various materials on said model should be, in order to extract 3D information from the image. So as the name implies, you're measuring stuff from photos. So in doing so, we take that same cone model. So this is why the cone geometry is implemented in the first place. You can just define a simple toy model for what we think the 3D structure around these low luminosity AGN, like the ones that the EHT looks at, are like. Essentially, this model is just a curved black hole. The idea is that we think the emission is probably coming from the jet walls. If it's not, it's probably coming from a thick disk. So we just treat it as a double cone. It's fairly compact. So the exact shape of the jet wall doesn't really matter too much. You know, if you Taylor expand, everything looks linear. And then we ray trace that. We think the emission is synchrotron. If you do that, you can then fit said model to the EHT data and extract information about the bulk space-time. Now, in order to actually fit the model to the EHT data, we have to, the Krang by itself is just a ray tracing code, so you can interface it. The modularity of Julia allows this to be very easily interfaced with Comrade. So just an example, if I define the jukebox model from that cone image that I showed before, it's just a couple lines to put it into Comrade. I just have to define what the intensity point is. It's a ray tracing code, so it ray traces to a point on the screen, and that's it. This is just all you have to do in order to interface it with Comrade. Okay, and once you do that, you can actually fit it to data. So this is just showing an example of said dual cone model fit to the 2018 and 2017 data. And you can see that once blurred to the EHT resolution, so the EHT image is shown on the bottom, and the model fit blurred to the nominal resolution shown in the middle row, and you can see they look very similar. But the models are also allowing you to get extra high resolution information that you may or may not believe, depending on how much you trust that. I can go into more details about that later, but just with respect to the code, one of the things that's beneficial about that, if you look here, this model has like 13 parameters, right? So one thing that all the people in EHT are interested in is what image features, like what features on the screen tell you about the bulk space-time parameters that you wish to study. And one of the things that's kind of nice about Julia is that I was able to make this automatically differentiable. I didn't really have to do anything. I just put enzyme into it, it works, and I'm able to create these saliency maps like people do with machine learning models, and I'm able to probe what features in the images are sensitive to the bulk parameters. So in particular, you can see that in the top row, the photon ring is evident, that like sharp ring feature, and the three things that stand out, the three parameters that are most sensitive to the photon ring are essentially the black hole parameters, the mass spin and the observer inclination with respect to the black hole spin axis. So that fits along really well with the narrative that people have mentioned before. Okay, so the next science case there's future VLBI experience. My advisor has been working on a potential space VLBI extension to the EHT called the Black Hole Explorer mission. And the idea is that this will help us get higher resolution images of a black hole. As I mentioned before, if you look at the saliency map, it seems like the photon ring is what is sensitive, or it seems like the photon ring is sensitive to the black hole's parameters, so the mass, the spin, essentially the space-time parameters. So what this implies is that if you have a really high resolution image, it should allow you to take very accurate measurements of the black hole space-time itself. In particular, if one is able to resolve that photon ring, then you should be able to do a black hole spin measurement. So it seems like there's this potential avenue for new black hole spin measurements that are agnostic to the black hole accretion. So again, I bring up this imaging geometric modeling approach. So if one were to do this, it'd be very hard because you kind of need to understand how to tie the black hole's spin parameter to the image features that you're looking at. But there's also this other issue, which is when I showed before the 2018 to 2017 fits, as you can see, the black hole looks very different between 2018 and 2017, or sorry, the fits look very different. But this geometric model itself is a model of the average accretion flow, and what this implies is that if you were to fit a model of the average accretion flow to data from different years, the variability in the years is appearing to order 1. It's kind of influencing your fit and causing your parameters to sway a bit. Not everything sways, but a lot of things sways. So the ideal situation is to kind of fold in this variability into the model itself. And the approach is that we're doing this kind of hybrid geometric modeling approach that encompasses that dual cone that I mentioned before. So the idea is that the dual cone model represents the average state of the system, and then we include an additional variability model which we multiply that dual cone model by in order to account for the turbulent accretion flows that generates differences in images. So what I'm showing here is just said model, and these are just random draws from the prior. So I'm just like drawing random things from the prior, and as you can see, they all kind of look like black holes, but they also have weird fluff around them. So this is just kind of a next step improvement. And this is very easy to implement. It was just, I didn't really have to write any new code. I actually just took Paul's imaging model and literally put it in the bulk space-time and ray traced that instead. Yeah, so just summarizing that, the idea is that jukebox is a good representation of the average image state. Simulations imply that variability due to turbulence affects your data up to order 1, so we want to incorporate that variability into the model. And this is preliminary, but this is just showing an example of said model fit to the 2017 data. So what's interesting, so again, I have the EHT 2017 image that's shown there. The consensus image in the middle, I have this from the literature, this primo image that's generated from doing principal component analysis under a GRMHD assumption. And on the right, I have this variability model, which is very, very flexible. So it doesn't make any assumption about GRMHD or anything like that. It can produce on aphysical images if it wants to. I think the thing that's kind of interesting about it is if you just look at it, there's certain features you can see. There's this brightness asymmetry that's kind of consistent. Oh, I think I put the wrong year. This is this is the wrong year's image. This is 2018. It should be this image. I'm fitting this year, the 2017. So the brightness asymmetry is there on the bottom left. So you can see that matches here with this variability model and as well primo. All the images feature shadow. But I think something that's interesting is this feature that's here on the southwest. Now, one of the things that's kind of nice about you interfacing this with Comrade is that one can do a Bayesian analysis. So, this is just a single draw from the posterior, but one can actually just look at samples from the posterior to see if any of these features are consistent or not in order to determine what we can actually say from the data and what we can't. So in particular, I'm just going to show a movie of the snapshot. So this is just showing draws from the posterior. You can see there's quite a bit of variability. And the point being is that each draw here is consistent with the EHT data. Each draw here is a possible instantiation that the system could have been that would have given rise to the data that we observed on that day in 2017. And the thing that's interesting is that you can see the photon ring moves in and out. Sometimes it gets dimmer, sometimes it gets brighter. So it's evident that we can't really constrain that too much. But there are certain features that are consistent. So in particular, we see that shadow is always there. We always see that brightness asymmetry, and we always see this fluff. And I think this fluff is particularly interesting because, you know, MH7 has a jet. The fluff this might be a sign of the jet wall. It may not. It could just be some fluff. Who knows? I think if I fit other years and we see that fluff persist, then that'll tell us about that information. And then this brings me to the last thing I'd like to talk about, which is multi-frequency jet modeling. So Randy had worked on multi-frequency imaging, and I think it's a good idea to kind of fold that into these existing models, which is again easy to do because of the modularity of Julia, but also put it into the bulk spacetime to just figure out what's going on. So recently there's been some advancements towards imaging the jet launching region of the black hole. So in particular, there's this Kim et al. Paper, which seems to suggest that we are now able to see where the jet is launching from the black hole shadow itself. So you can sort of see, you know, you see a dot, you see a shadow, and you see the jet attached to it. But strangely enough, the 230 gigahertz image from the AHE does not show this feature. But it might be there. It might just be that we need more robust models and better priors in order to extract the information. And I kind of flashed this geometric model again. I think this is kind of the avenue to go forward in order to understand what's going on in that system. So I think the benefit of this over some traditional approach like GRMHD is that you can just easily swap out the material, can just easily swap out the geometry, and just see what is consistent with the data and what tells you what's going on. And that's it. Thank you. If anyone, that's my GitHub link to Krang. If anyone has any questions, please don't be afraid to ask.
Fantastic talk. This is really, really interesting. For the ray tracing part, are you able to utilize the traditional graphics pipeline units in GPUs, or because this is ray tracing, different kind of geometry, you just have to do it manually?
Yeah, so it's where I use it. So Julia only has access through the compute shaders. They only write wrappers for the compute shaders essentially, but it doesn't matter. It gives you the same performance, just that you kind of have to approach a problem a little bit differently from how you would with a normal graphic shader, but it kind of doesn't matter anyway because a graphic shader would render to the screen, so it wouldn't be too useful for you for scientific analysis anyway. But yeah, it's essentially just the same as, well, I'm not actually writing in the shader language, I'm just using, it's essentially just you import a CUDA array or a metal array and you broadcast over it.
So maybe I haven't fully understood what you showed when you showed the saliency map, but is it possible to show a saliency map marginalized over something that you don't understand in your Bayesian model, and as an extension then make better choices about what visibilities you really need to prioritize to improve your posterior estimate on the parameters of actually interest?
Yes, that is, sorry, I'm just looking for it. That is true. I think, so this saliency map was kind of constructed because I think it was just sort of, it was constructed out of this want of if someone gave you a picture of a black hole and, so you wanted to point to them at a feature to study in order to extract some information about accretion or something, what would you look at? So this is kind of the most agnostic thing. I think in principle you could pick specific directions in constructing the saliency map and marginalize over variables in order to get more, I guess, accurate features under certain assumptions.
But could the saliencies be propagated all the way back to visibilities as opposed to the image?
Yeah. So it can okay. Maybe I misunderstood the question. So this is a saliency map in image space. So what I could have done is that I could have constructed saliency map in visibility space. And yes, it would propagate that way, yes.
Yeah, this may be incorrect. Have you ever thought of using geometric algebra and to do your calculations?
Geometric algebra?
Yeah.
No, I've never.
And conformal geometry.
I haven't tried it. No, I should. I'll try and give it a
You know,
look.
there's Geometric Algebra for Physicists by Chris Doran. He gave a talk a couple of years ago at JuliaCon about how he's trying to use geometric algebra to improve ray tracing.
Yeah, I know you've mentioned it before. I keep forgetting to look it up, but I should look it up.
All right, let's thank Dominic again. Next up is Andrew Sadie.
Pause. Okay. Am I okay to move forward a little bit if I want to see the screen? Yeah. Okay, I'll do that. Can you tell me when you want me to start?
All righty. You can go ahead and get started.
Okay, all right. Hi, everyone. My name is Andrew Sadrie, and today I'm excited to tell you a little bit about our work on building an end-to-end spectral reduction pipeline for Apogee, of course, in Julia. So just to bring everyone onto the same stage, Apogee is a set of two nearly identical instruments placed in both the north and south, so we can get all-sky coverage. And as spectrographs, the main goal of these instruments is to provide us measurements of flux versus wavelength. So like the plots shown over here on the right-hand side of the screen. And so when I talk about making a pipeline, I'm talking about going from the raw data coming off the telescopes all the way to the final data product of those spectra. Right, so when I say end-to-end, this is just an overview of the data flow that we've currently set up through our pipelines. So there's some raw data taken at the telescope. That data is taken on different objects that the operational database tells us that we were pointing at, and we interact with this through a package called Almanac that dumps all of that information to disk in an HDF5 file. This allows us to build what I have termed the Great Wall of Julia. This is somewhat of a joke, but also I think it's quite important when you think about having reproducibility and interactivity and accessibility for people who might be language divergent users like myself. So after that stage, we have two main pipelines that I'll tell you about today. Apogee reduction.jl, which takes us to 1D spectra from the raw, so I'll tell you a bit about that. And then armagics.jl, which does component separation to separate out the contribution from the stars and the Earth's atmosphere and a bunch of other stuff. Okay, right. So Apogee reduction.jl is a collaboration between myself and 3 other people on this screen, one of whom is Adam, who we'll be talking later. And this will tell us about the first stage of that data reduction. There are many steps that I do not have time to tell you about, but if you're interested in them, we've implemented cool algorithms for them, and you can talk to me about that afterwards. Okay, and before I jump into what we actually did, let me tell you slightly why we did it. Apogee's been around for over a decade, so you might think, why would you rewrite a package that's been optimized over that length of time? One of the answers is speed. It's much faster. It's a little bit difficult to quantify how much faster, but I can show you some benchmarks. It also solves what I call an Astro N language problem. I mean, the package was written half in Python and half in IDL. Instead, now we have one single performant language called Julia. As a new user to the package back when I started trying to work on Apogee, I found it very difficult to enter, and I find it's very difficult for my students to enter. It's over 4 million lines of code. Instead, ours, last time I measured, was less than 8,000, and I think we could actually be smaller than that, not larger, and it has the same functionality. And then finally, we were able to implement a bunch of new algorithms and trace down systematics that were bothering us for years. Okay, so that's why we did it, and I'm just going to show you a couple of the different algorithms that we implemented. So in the near-infrared, a lot of our detectors have non-destructive readout, which means that we have arrays of pixels that are imaging the sky, but instead of just taking an image, they ask how many photons you have in a pixel as a function of time. And so you have this constant increasing number as you get more and more photons in your bin until you reset and you start again. And so when you want to measure how much flux you got in a given pixel, what you're actually doing is something like a ramp fit or like a linear fit. And if you want to do that really properly, you have to account for the fact that read noise at an early time actually impacts the measurement that you get at a later time. That imposes a lot of correlation. You can reduce the amount of correlation by looking only at differences, and that gives you a correlation structure which is really simple. It's just a tridiagonal Toeplitz matrix. So you just have these three diagonals that are correlated. And we have ways of doing inversions of those, either using recursion relations or actually in this package we do some fun Woodbury identity stuff. Okay, who even cares as the astronomers in the room? What you should care about is the fact that if you plot the signal to noise ratio versus the flux in a pixel, the improvement that you get relative to a conventional method is what I'm showing on the y-axis here. And it's for the typical range of fluxes in our survey, somewhere between 6 to 8%. So it's like you just had 6 to 8% more time on your telescope. And given how expensive telescope time is, that's quite important and impactful. Okay, a very classic calibration you have to do in astronomy is calibrating your pixels with respect to how they respond to photons. Some are more responsive and less responsive. This is called a flat. And for the first time, we had the capability of doing these very, very flexible illumination models. And we built up just a basic arbitrary but high-dimensional cosine and sine basis that allows us to fit out the fact that the lamp that we're using to illuminate the detectors isn't actually very uniformly illuminating them. And when you remove that, for the first time, we see these like really interesting structures that hadn't been seen in the flats before. These are things that you absolutely want to remove. You do not want them to be in your data, and we can do that now. And it's a work in progress for us to shift to finufti.jl for faster non-uniform Fourier transforms for this modeling. Okay, a somewhat intermediate 2D to 1D stage is wavelength solutions. So you generally do peak fitting for sets of lines or features in your spectra that you might know the wavelengths of. That's an absolute calibrator. We actually have several stages. We have absolute calibration, then we have relative calibration, where you don't know the exact wavelength of a given peak, but you know the spacing between the peaks. This is very commonly done with Fabry Pro interferometers. That leads to a very dense set of tiling of the plane of with these different Fabry Pro interferometry peaks, the residuals of which are shown on the left. And then we do per fiber observational tweaks. And so we're getting to about 60 meter per second precision on a single peak centroiding as shown by these residual maps. And we implement this by carefully trying to parameterize most of the problem as being as linear as possible, and then we iterate between linear and nonlinear updates with optim.jl as we go through this procedure. Okay. One calibration that we do at the 1D stage is relative fluxing. Every time you unplug and plug your instrument into your telescope, you have to recalibrate how much light is actually getting through the fibers into your spectrograph. We have 300 fibers, that's the x-axis here, so that's 300 different stars that we can look at. And some of them have good throughput and some of them are broken, and you need to know that number and divide by that essentially. And I also want to highlight the fact that we have really nice integration with slackthreads.jl. So we post every night the fibers that are broken or in warning status, which allows us to interact with the operations team to tell them what fibers to fix. And actually, we are currently fixing fibers at APO as we speak. We also use the Slack integration to post a lot of our quality assurance plots to make sure everything looks good every night. We either post them directly to Slack or to an HTML dashboard. Okay, so the second part of the talk, I just want to talk about armagics.jl. This relies heavily upon low-rank ops.jl, which is a package that I also wrote during my PhD. And the basic motivation for armagics.jl is that ground-based spectroscopy is hard because you have to look through the atmosphere. And so, you have these emissions from different molecules in the atmosphere, they absorb and emit, and it leads to what is essentially a component separation problem. So you have both the atmosphere, the star, and anything between us and the star that you're trying to actually model. And so we decompose an apogee spectrum into a bunch of different components, some to do with the sky, some to do with the star, which we build using priors that are mostly data-driven, sometimes hybrid theory and data-driven priors, an ISM absorption component, and then a residual. And we do this decomposition with a Bayesian component separation technique called magics that I don't have time to explain, but basically uses a bunch of really fancy linear algebra and matrix speedup tricks. It sums exactly to the data, so there's no information loss. You're just partitioning the data between these different priors and your expectations of what the contributions of those are to your data. But you know exactly all the counts that you got as a function of wavelength are still here. You just have to figure out where they are. And it scales quite nicely. So it scales to all 2.6 million visits of apogee, and it does it quite fast. And so I can tell you about the tricks to make it fast, but it's around 7 seconds a star. Okay, and I have only one science case that I have time to tell you about. It's the simplest to look at as a metric of success for astronomy, and it's measuring radial velocities, just like how fast something is moving away from you or towards you. And you can see this has huge implications for people who think about exoplanets, stellar structure, galactic dynamics, and the like. But this is just showing you that out of our pipeline, if you look at repeat measurement velocity scatter as a function of signal-to-noise ratio, it plateaus at your precision floor. And the previous pipeline plateaued at 43 meters per second, and we got down to 30 meters per second in terms of our velocity precision. And these are uncertainties adding in quadrature here. So this is like a pretty big improvement. And this is actually what the spec of apogee was supposed to be. And for context, that's saying that we can measure shifts in the wavelengths of our spectra at 6/1000th of a pixel, which I think is just like the physical pixel on the detector, which is kind of fun. Okay, so we actually do the reductions in 2 modes. One is daily mode, where we run it with airflow plus Slurm cluster managers per task, and we run this DAG, and slightly more complicated DAG sometimes. We're thinking about switching to elastic cluster managers to have more persistent worker pools. And then sometimes we run it in a bulk run mode, where we reduce all data from the beginning of time, which is 2011, and we use Slurm cluster manager in a very bulk multi-node context, and PMAP with some careful exit codes to do restarts. And we do per fiber batching to handle our priors. Okay, so what I've tried to tell you about today is the fact that we have written an end-to-end pipeline for a complicated and long-running instrument. All in Julia, it handles raw telescope data going all the way to the science data products, handling complicated sets of calibration files from nightly to monthly. It has all the automation and conveniences that you might want, post to Slack. And the speed and simplicity of Julia has allowed us to implement what I think are really cutting-edge algorithms for spectral reduction that I think will be the future of how people do this sort of work in astronomy. So be happy to take any questions. Thank you.
Yeah, comment. Why don't you make this a vast talk?
I'd be happy to make it a
vast talk.
Yeah, sure.
Yeah.
All righty then. Next up is Sasha Plavin on Astro Catalogs.
All right. Hello, everyone. Today I will be giving a non-research talk, but going through how we can manipulate tabular and a little bit on images, how we can manipulate really like astronomical catalogs in Julia, and discuss some kind of design choices that go into it. really, why kind of all sky catalogs, why I'm talking about them here, because no matter if you do galactic, extragalactic astronomy, no matter what wavelength range you use, you often need to work with catalogs, like survey catalogs, survey images, and stuff like this. Maybe I'm personally, maybe I'm working with all sky catalogs more than an average astronomer, but still, I think it's common in many fields. I would say that in the past few years, we've seen Julia ecosystem, both in general and for working with astronomy catalog specifically, it's been maturing. It exceeds Python counterparts in some cases, but still some pieces are more difficult than they should be or they are missing. So in this talk, I will give just kind of a few examples, a walkthrough of how to kind of get access to some like all sky tabular catalogs, how to plot them nicely and conveniently, how to cross-match them, and how to cross-match them with images as well. And then I'll discuss a few words on like how to design your functions and data structures for extensibility. First of all, obtaining data. I really like that in Julia you don't really need like custom fancy data structures for a lot of things, including astronomy catalogs. They can be just kind of lightweight Julian tables, basically in the simplest case, vectors of named tuples. So unlike what AstroPy does, AstroPy like has a special AstroPy table type that is not the same as pandas, not the same as like NumPy. So in Julia we just don't need that. We can very easily use the built-in structures. So here I show an example of, I hope it's visible. Yeah. So an example of how to access virtual observatory, like catalog available with virtual observatory protocols. You can use arbitrary SQL expressions. It's the same execute from DB interface that is in Julia. And then the only astro-specific part here is really, astro-specific type here is a sky coordinates objects. Otherwise, it's kind of what you generally do in data manipulation. Of course, sometimes you have catalogs as, oh yeah, and I forgot to tell that in virtual observatory you have the benefit that all units, everything is automatically parsed correctly, so you don't need to care whether like your coordinates are radians, degrees, seconds, or whatever, they always are correct. You need to be a little bit more careful when loading catalogs that are just plain CSV files. That is also very common, and I think like it's the best practice, but and I really encourage everyone to follow something like this. Is immediately when you read a catalog or any other data set, really try to convert the values you need to proper units or types. Like here, for example, I load an IceCube catalog of IceCube events, and I immediately convert it to like just raw columns with array index to sky coords. I create the kind of coordinate uncertainty. So for your purposes, it may be like just add units or use your other kind of like domain specific type. But this is nice to do at the first place immediately when reading, and then don't care much about potential issues downstream. So plotting is I think is a very strong side in Julia here, because most notably sky coords and also uncertain.gel have direct integrations with Makia. So you can just plot your sky coords objects. You can plot them with GeoMakia as I'm showing here. You can plot them like with regular access. And it works like for lines, as I shown with a galactic plane. It should be kind of straightforward to see what's going on here. And for source catalogs, and this is kind of a great example of also if you have a type that makes sense to plot at all, just add convert arguments for Makia. It can be easily done in your package extensions. So GeoMakia is just the current way in Makia to plot in spherical coordinates. It has some sharp edges, but for lines and scatter plots, it works pretty consistently in my experience. And of course, given that it's Makia, you can just explore the plot and zoom it in. It's just very seamless. Nothing extra is needed. This is built into Makia. Okay, as I said, plot recipes for everything, not just coordinates themselves, but coordinate uncertainties. So I just call poly, and there is a recipe that's saying, okay, how to convert coordinate uncertainties in the sky to polygons for plotting. That also works seamlessly. Then cross-match. Flexi joins is a package I developed, and I will be giving a dedicated talk tomorrow. It is like for joining all kinds of data sets, from simple key-based joins to cross-matching like Sky catalogs. Oh. So arguably it's the most featureful among fast joining libraries in any language. At least I haven't seen any alternatives. It's designed for both flexibility and performance. So for example, I use it also to perform like Monte Carlo simulations, let's say like perform a Monte Carlo simulation 1 million of times and can calculate some p-values. Whenever I kind of describe it to other people using Python for that, I always hear like, oh, really, it runs in like just 10 seconds for like 100,000 or 1 million iterations. We need to run it overnight. They use some AstroPy tools, and probably they also have some other inefficiencies, but anyway, this is like really designed to be flexible, but also performant. And of course, after doing the cross-match, you can plot the cross-matched object, you can plot like text labels and everything. And what I really like is that you have this, in my case, you have the same code, the same recipes, everything. If you use GLMikey, you get this interactive exploration thing and faster plotting in general. Then if you like tweak some visuals and want to save this plot as your kind of publication quality plot, you just switch to ChiroMikey and it's almost seamless. You don't really need to do anything. That's for tabular catalogs, for Sky images, and especially for all Sky images. There is also the package I developed, skyimages.gl. It supports all kinds of things with the same interface, from all small fields to full sky, both fits world coordinate system and hill peaks with the same interface. You can, so this is a firm image. You can, of course, just plot it. Image plotting with GeoMikey breaks from once in a while, so it's fiddly. How it works? It is really kind of, image is a keyed array from accesskeys.gl for maximum interoperability. It's not a custom type. Custom types only appear inside for access keys. Okay, of course you can look up the image at any coordinates. And almost my last slide, regarding designing your data structures and functions for extensibility. I would really argue for using generic containers as long as possible. For example, not custom my table, but like vector of name tuples or struct array. Not custom my image, but keyed array, and so on. And of course, sometimes you need to introduce custom types. I argue that they are better introduced at the innermost level possible. For example, not like sky coords with circular uncertainty, but just circular uncertainty and use uncertainty packages that support every, like, that are flexible enough. Not world coordinate system based image type, but VCS based lookup type for that image. There are exceptions, but I think these guidelines help with interop that is crucial for kind of success of Julia and stuff like this. So to sum up, really, I think that we have a rich Julia ecosystem for working with astronomy catalogs and data sets, from tabular catalogs to images, from data access to analysis. Both astronomy-specific and general-purpose packages can be used for that. There are some pieces missing here and there, but I find that it's easier to fill them on my own in Julia than if I was missing something in Python and wanted to implement it and make it fast. That's why I really encourage package authors to keep extensibility in mind as potential like educators, people working with students, to promote like tinkering and understanding algorithms, how they work, not just the user-facing interface. That's basically it. I didn't say anything about VLBI today, but I have a poster on VLBI data.gl and the companion packages showcasing the functionality and some interactive tools that are kind of like end-user facing. That's it from my side, and I'm happy to answer any questions now or in the discussion sessions that will be starting soon, I guess.
Questions for Sasha?
Okay, great talk. Yeah, one of my questions is actually related to your table join. You know, a lot of big surveys, especially LSST, just to name one that's open at the moment, are spending lots of money to rewrite new softwares for new table types and database types, just to do cross-matching multiple epochs of observations to build up detection catalogs. I mean, is this so performant that we should just do this instead? I mean, does this replace a huge database for a survey like that? What is the limitation? What's the breakpoint here?
So FlexiJoins itself, it works on in-memory datasets. For out-of-memory, I mean, support for SQL is pending with SQL collections.jl. With DuckDB, I think you can do a lot. Out of core is, I mean, I don't have like an experience in implementing out of core algorithm myself, but interfacing to DuckDB is potential. Also, I didn't show it here, but you can do cross-match with some tables that is available remotely on the virtual observatory server. I use it with Gaia sometimes, for example. I don't want to download the billion of Gaia objects.
On a related note, one thing that some of us in the doing population analyses kind of pine for is being able to do probabilistic catalogs, where maybe you have objects which are clearly detected, but then something in the middle where there's lots of low signal noise detections. And is that something that enters into this at all, or in the future?
So I would say that the FlexiJoins itself, it is for joining on some deterministic predicates. And as I understand, whenever you are talking about probabilistic joining algorithm, the first step is to have a deterministic join with some kind of relaxed criteria, and then refine it with probabilistic arguments. So this is for the first step, because there are so many choices you can make on the second.
Makes sense. We actually have a bit of a gap, and so I'd encourage people, we can ask questions, rather than just like sit here in silence for 10 minutes.
I think it's also, we wanted, yeah.
Oh, was there another question?
No, he was going to give a talk. Right?
Oh! Oh, great, okay. Excellent. So then, let's thank Lasha again. And, okay.
Oh, yeah. Oh.
Yeah, so just last second change, we realized we had an open slot, so we're adding an additional talk by Adam Wheeler from the Flatiron.
Yeah, thank you. Thanks for, I signed up for this conference like 2 weeks ago, so like way past the application deadline for talks. So thanks for letting me talk anyway. You know, caveat, this is, you know, I made these slides this morning, so apologies for that. But I think hopefully it'll still be interesting. So Korg.jl is a package that I develop. Most stuff that I work on is related to it in some way, and it does basically the theoretical side of what Andrew was talking about. So you have a bunch of spectra, and you're interested in what they tell you about stars. I have a diagram of that here. There aren't actually any instruments on this telescope that produce spectra like that, but you get the idea. You know, you get the raw data, you analyze it with Andrew's excellent tools. You get beautiful 1D spectra that are like, you know, on a wavelength grid that you understand. Now you want to understand them. The way that you do that is with a theoretical model that goes from, you know, parameters describing your star to spectra. And that's primarily what Korg is. That process is traditionally called synthesis. Just a bit of lingo there. I also do some of the fitting. I have opinions about how to do that. Happy to talk about it. It's maybe not as straightforward as I hoped it would be when I started working in this field, but I'm going to talk about the forward model part of this today. Okay, so a little bit of context. Why is this worth doing? Basic sort of stellar atmosphere model, stellar spectroscopy is pretty well understood. So Cecilia Payne figured a lot of it out, and at this point that was over 100 years ago. It's like actually a very mature theory in astrophysics. So like on the one hand we have that, on the other hand we have a lot of data. I mean, like, you know, many other areas of astronomy now. It's not like a you know, a radio interferometry amount of data, but it's still a lot of data, and so it helps to have good software. These are some surveys that are producing lots of data, some recently concluded, some upcoming, some ongoing, but we have like tens of millions of spectra that we need to worry about. And there are also substantial analysis problems. So, you know, if you've seen talks where people talk about spectroscopy and problems, the things that have likely been mentioned are sort of like scientific assumptions that people make in the models, like science assumptions to simplify things. So local thermodynamic equilibrium, 1D models, and people talk about these as being like the sources of error, the things that we have to move past. That's right. I mean, we do have to move past those. But there are actually, those aren't the only things that are actually sort of causing problems with the, final like tables of stellar parameters that people work with today. Big surveys have to write pipelines that can process tons and tons of spectra. With the tools currently available, they have to make massive computational compromises, or massive scientific compromises, let's say, for the sake of computability. So this is not to pick on either of these surveys. And I dropped some other plots from this talk showing similar things, but this is just comparing aluminum abundances from Apogee and Galah. I think this is Galah DR3, not the latest Galah DR4. So these, and for a set of stars observed by both, they should match. They really, really don't. What's going on with that? And I contend that a lot of this is actually, sort of computationally, based on computational problems. Okay, so Korg is, like I said, an open source tool for doing these calculations. It's the first one to be written completely from scratch, I think, since the 70s. I guess there's now one exception to this. There's another recent package called Stardust that's written in Python that's a bit similar, but until Stardust, Korg was the first to rewrite in a long time. There are some other packages from the 90s, so if you know Spectroscopy Made Easy or TurboSpectrum, those are more recent than the 70s, but they also do use some of Bob Caruse's Fortran routines. Okay, docs and tutorials on GitHub. You guys know this. It's Julia conference. It's quite fast writing it. Starting over from scratch with sort of modern computers in mind. That have like a lot more RAM than they used to, and focusing on speed has made it fairly easy to be the fastest thing available. So here's for a fairly representative thing that you might want to synthesize. This is 500 angstroms of an Apogee spectrum for different stellar parameters with some different tools. There are some other ones that are not on here. I'm not aware of anything that's faster than Korg. There's other tricks that I've done since then. This is like a little bit out of date. I don't think anything's moved around a lot, except if you have a synthesis, a star that has a lot of molecular features, I have some tricks where I'm now, you sort of get an additional 1 to 2 orders of magnitude speed up there. Okay, and also autodiff. It's great. Everybody loves it. If you're doing any kind of, anything where you need derivatives, you're, maximizing a log likelihood, for example, because you want to know what the parameters of the star you're looking at are, having derivatives is great, and we can get them with autodiff. So this is, in my case, this is forward diff, because thankfully, in most cases, I'm talking about fewer than 20, maybe many fewer than 20 input parameters. So it's totally reasonable to use forward mode automatic differentiation. Thankfully, that's much simpler to implement. Especially with Julia's sort of multiple dispatch model. So forward diff works great for my use case. Here's an example of how it works. It's pretty straightforward. This is just, I've recently been trying to make it easier for people to use without learning much about the internals. So I have this single entry point, call synth, describe the star, it gives you a spectrum. This is how you use it. If you call this with JuliaCon in Python, the code is actually identical. Except for the semicolon, I think. Oh no, I didn't write it with a semicolon here. Okay, so it's actually identical. So this is how Korg works. I'm just going to quickly walk over it. I'll touch a little bit on the Julia packages that I'm using. This general framework is true of other things that you may have used. The inputs to the problem are, along with a description of the composition of the star, the abundances. You have the model atmosphere, so that's some thermodynamic properties as a function of depth. Again, we're assuming that it's sort of spherometrically symmetric. We're just describing a 1D structure, and then also a line list. So, quantum mechanics isn't solved. We don't know all the transitions of all atoms and molecules, so we think of this as something that the user might want to configure. Those things are described by the line list. Take those as inputs. The first step is to do the chemical equilibrium. So at each layer in the atmosphere, you have sort of different conditions, a different temperature and pressure. You want to figure out how much of every species there is. So a species here is a specific atom or molecule with a specific charge. There's a few hundred of them. So all the elements from hydrogen to uranium, and then a bunch of small molecules as well that are important in stars. You set up a bunch of equations like this, and then you solve them. I solve them with optim.jl. This is a good example of something that was actually very easy to write in Julia, and the number of lines of code is minuscule compared to the Fortran implementations that people have had to do before. it's a really good sort of, example problem. Okay, then once you've done that, given the sort of detailed composition everywhere in the star, you want to add up the opacities. There are, we often break opacities into, continuum sources and lines. Here I'm showing, sources of continuum opacity that Korg is sort of taking into account as I can play it again maybe. This is going from a very cold star to a very hot star. So, hydrogen becomes comparatively more important. Metals become comparatively less important. All the structure stuff is like resonant interactions. And then there's also lines, okay? So, this is actually the slow part in almost any of these codes for most syntheses. Atoms, especially molecules, have like a lot of lines. It's not unusual to have tens of millions. And so actually just computing a bunch of Voigt profiles and adding them up is the slow step in Korg, and I think in all of the other codes that do this calculation as well. So spent a lot of time working on a fast Voigt profile. It's not perfect. There are things about it that I would like to be better, but it is pretty good. We also speed this up with multi-threading if you launch Julia with multiple threads. And like I mentioned, you can do some tricks with molecules where you can pre-compute some cross-sections and interpolate them and save a lot of time that way. But this is the part where I've spent the most time staring at the flame graph, trying to make it fast. Okay, and then finally, once you have opacities, you do radiative transfer. This is comparatively easy, almost never the slow part. And yeah, I have more I could say about that, but I won't get into it now. Okay, yeah, thank you. I can talk more about specific science things, but I think it's maybe too detailed for this conference. While I was watching everybody else's talks, I thought maybe I should put in some sort of pros and cons for Julia. So as a language for me to use to write the package, I love it. I think the sort of model of just-in-time compilation plus multiple dispatch is perfect for scientific computing. The hard part has been, I think two things. One is that compared to Python, obviously the ecosystem is not as mature. There's no massive tech companies that are maintaining automatic differentiation infrastructure, for example. That's a challenge. Thankfully, forward mode is very good for my use case, so it's mostly not a problem, but I think it's a thing that I see as a general barrier to adoption. And the other thing, of course, is that people don't want to learn a new language, as everyone here knows. I think getting interest and even adoption from sort of large collaborations where people have a lot of data and they care a lot about the performance and they're not expecting it to necessarily be that easy has not been super hard. But I'm also trying to support people who want to have they have a dozen spectra and they want to analyze them. That's still a massive use case. The other existing tools I think are, some of them are scientifically very good, but they're definitely difficult to use. It's an area where I feel like I could, it should be easy to replace them, but in practice, I think I need to spend more time on good, easy to use Python wrappers. So yeah, thank you.
Okay, I think we have time for a couple of questions. Yeah, Sasha.
I think that, I have finally accepted that I need to write a Python package that people can pip install or UV pip install, and then use it, use Korg without any other effort. I think once I've done that, I may have a more nuanced opinion for you. But I mean, I guess what I mean by this is my current approach has been to tell people this is how you set up JuliaCon. It's not hard. Here's a tutorial notebook where I'm doing it in Python with JuliaCon. But in practice, I think particularly with the setup, people have a lot of difficulty. And then also with just the data type conversions, simple stuff, but it's, yeah, things like that.
Paul.
Did you roll your own Voigt profile, or are you using the algorithm from 1982 or 83?
I am using an even older one than that.
Oh,
yeah.
okay.
Yeah, I can't remember the citation off the top of my head.
All right.
Any other questions? Okay, if not, I want to invite all speakers up to the front for the discussion. There's going to be most of the room.
Well, at least come to the
quite a bit of observations. But
Sorry?
We also have observations.
Yeah.
Okay. Okay. All right. So there's a few of us here, but I think an idea is, I think what Eric had said was maybe we have a couple points that people wanted to discuss, and we can start a little bit of a roundtable discussion. And then because Eric's the leader, I'm going to put Eric on the spot and give us the first few topics.
Okay, well, I think we had one suggestion was maybe how to get people more quickly ramped up into Julia, both as the trying it and also as the incorporating their workflows. I think some of the things we talked about to help us get there might be identifying things that are so valuable people are willing to invest the effort, and where are the things such as, whether it's coming up with some core packages that are really fundamental, or whether it's having some end-to-end packages that do everything for you, or where are some opportunities where plugging a few gaps might make a big difference in terms of the audience use cases. Maybe relate your point, some education things. I mean, I know Penn State has this summer schools, and we occasionally do a second week. There's a whole set of tutorials from machine learning, optimization, SciML type stuff there. I teach classes in data science and hypermesh computing that have maybe 16 labs or something that people can borrow. And Paul runs a AAS workshop. So there are several things, but maybe they're just, you have to be in the know. And so maybe just setting up a Git page with links to all these in one place would be something that we could do there. There's probably an opportunity for, instead of people just, an opportunity to have maybe a feature request, like what tutorial would someone really like, right? And I find that often, if you just say, I'd really like a tutorial, gee, there's lots of things I'd really like. But if you say, I kind of want this because I need it, and if you could help me do my research, I can make the simplified version for other people, then maybe you get an energetic grad student who can, kind of do some of the work, and then a few people from some more experience help guide them. I think that might be a good venue or good avenue to help flesh those out. I think someone mentioned funding challenges. That's, it's not looking like it's going to go away anytime soon. But I did have one question for the, can someone quantify either Apogee or EHT, how many more dollars would you have had to spend to buy a telescope to make as big of a difference as we got out of investing in software, right? I mean, it's a little bit ludicrous, it's probably astronomical. But maybe, for us that's obvious, but maybe for the people who don't quite get it, being able to give some examples of, the extra precision we got out of Apogee would have required a telescope 30% bigger, or EHT would have been so many $1 billion more, or whatever, might be nice little bullet points when we are trying to make the sales pitch. But those are just some things that I either heard or thought of, and I'm happy to get other people to suggest topics and see where they want to go.
So it's indeed a kind of curious topic about making Julia more popular. I'd like to share a short story. Is that recently I kind of noticed that I make quite a few kind of interactive plots for different reasons, and I started just a few months ago packaging them in some self-contained, relatively user-friendly software, and just recently I had quite some success with kind of a relatively simple tool. So you have multi-frequency VLBI images and already prepared, and you want to align them. And this is kind of a non-trivial process, and there are some Perl scripts in the wild. I know people who just do it kind of manually by choosing points in the image, and recently I kind of shared this kind of jetalign.jl. It actually featured on my poster later this day. It's the same VLBI data poster. Kind of the first response I got when I kind of you are working with multi-frequency image alignment. This is a tool. It's user-friendly. You can play with it, see how it looks, and save the results. First of all, first response I got is oh, I'd be happy to use it, but it's probably very difficult to install. Then I had to show 2 or 3 people that it's really seamless. I got Windows and Linux. I don't think and I myself have macOS, so yeah, it's all 3. And it is really seamless, aside from I had a simple typo in the docs at first, but other than that, everything went smoothly. People like, oh, really, it's so simple to install. And now there are at least several people kind of using this tool. And by default, they are not Julia developers. They are not writing Julia code. But if some of them wants to change something in there, maybe add some feature, or maybe like in a few years, like the requirements change, and they will either need to ask me, like find me somewhere, or like look at the code. It's not a long code, it's not a complicated code, and just fix it there. And I think this is one way kind of to get some Julia users and developers in the medium term.
Kind of on the aspect I was thinking about, kind of why certain languages are very popular for economic reasons, but people also gravitate to certain languages, I think, more so than others, and is trying to figure out what exists in those languages ecosystem that causes that to occur. And I think one of the things that JavaScript and Python has in particular that's kind of similar to what Sasha was saying is that they have these playground ecosystems where, you know, if you want to share, say, a notebook, a lot of websites just allow you to just run the notebook on some server online. You don't have to install anything, it just runs. Apart from that, there are also websites like Observable HQ where people just upload their data analyses, and they're just interactive plots and interactive packages that you can include that are either JavaScript or Python. And this kind of allows people who have just kind of a glossing interest in the language to just look at the code and look at how it works and what it produces. I think something like that for Julia would be good, where you could just go on the website, just play around with little snippets of things and edit it and WebAssembly, yeah.
Okay. So, I mean, there is Julia Hub, which makes it pretty easy to have Pluto notebooks hosted. The problem is that there's a dollar figure attached, right? And so, like, there's a reluctance to just say anyone in the world can, use my notebook on my account, right? So, yeah, like, and so this is no longer a technology problem, right? Like, we can host a notebook, we can make a static version of it, Pluto one that it's really just like clicking two buttons. So we can solve like 90% of it, but yeah, I'm not sure. Yeah, it doesn't seem like a technology problem. It seems like a economic problem.
Yeah, I'm gonna, I actually think we're pretty good at some of this stuff. I think we're resource limited at this point in terms of development as well. Like, resources to develop packages are hard to get by. We've been struggling with getting funding, at least locally, and I think the most success we've had recently is going private, so like with Amazon and stuff. But like, it's still like, there's lots of things I can imagine for us to improve stuff, but it's still, we're relying on postdocs and PhD students a lot of the time as part of their side stuff to develop these packages and to develop tutorials. I think workshops are fantastic, but someone's got to pay. Someone's going to have to pay for people to come to go. So there needs to be some amount of like funding for a lot of this. I know it's not a exciting thing to talk about, but money's important, especially for pushing some of the ecosystem forward. So if people have good ways or like lines for funding for specific things, it would be really good for us to know to try to grow this, grow the ecosystem and just grow.
How does it work in Python?
How does it work? Python's different. They have like huge corporations.
For Astra packages?
For Astra, well, I think that's the other problem is that Astra Python is just soaked up all the Astra. Like I've been declined. We've been declined for funding proposals because they're specifically like, oh, we just want to fund Python packages instead and keep putting money into like AstraPy.
Yeah, definitely not disagreeing with any of that. Absolutely. But I guess one of my questions is like, how much do we think we haven't done just because it isn't all in a centralized place? Like, I think compiling all the resources and tutorials and code snippets that everyone here has run and just like put them all in one place, put them all together, see what we have done, and maybe the gap isn't as big as you think it is now just because we haven't compiled it, or at least, I don't know. Oh my God, I said compile, stop. So, yeah, maybe that'll at least make the problem clearer, and then if it's As you would say, if we're hosed, we're hosed. But at least it will be clear how hosed we are.
Well, okay, so there may be a bit of a marketing issue, right? So AstroPi lumps everything together in one big headline name that makes it easy to say, oh, AstroPi has all this impact, right? But how much has this subroutine had, right? No one has any clue. Right, Julia has a more composable mindset of, oh, there's astrometry.jl and fitzfiles.jl and barycentric corrections and like everything's so micro. And so, I mean, it's a little bit awkward to like even just cite 50 package dependencies in your paper. So we all might not be perfect about it. But further, each of those individually seems small. But I mean, I'm thinking like the SciML organization, for example, has dozens of small packages that collectively are a behemoth. And I think they have had some success getting NSF funding. Now, they probably didn't go to astronomer panels, but perhaps some degree of, I mean, there's the Astro Julia organization, but I mean, somehow in the marketing of what we're doing so that we could put forth proposals that we could point out how it's had a bigger impact on disparate communities, like VLBI and like cosmology and like apogee and like EPRV and kind of get that combined benefits.
Yeah, well, I mean, it really goes back to resources. I mean, you know, we have next Wednesday is Astro Julia, a Zoom meeting, and you know, when you only get a handful of people showing up, and it's pretty much the same people all the time, it's just very difficult to keep things going. You know, and I realize we're all busy, but if we want to move it forward, we really have to make an effort to have, you know, the Zoom meetings got to be bigger. We've got to organize, you know, better. And that way, you know, we can move forward. You know, that's the one aspect. And the other is, you know, when we were developing, you know, Python 30, 25 years ago, we decided, you know, we knew we had certain basic fundamental things we had to do to get it established. And, you know, and that's the, you know, astrometry.jl is one of those, fitzfiles.jl is another one because, you know, people use that. And there are other applications that we need to develop and just have there. I mean, it's, you know, I've gone back and I've looked at, you know, AstroPi and compared what we have, and we're about halfway there. And I would think with, I don't know, a few man years really, you know, a few people working, that we could catch up to them within a year if we just had people actually working on developing and filling that stuff out. And then the other aspect is, you know, to go back, we don't want monolithic packages like AstroPi, but, you know, the Julia Astro webpage does have to organize things better, and we are working on that now. But just to say, maybe we need a high-level package with sub-packages, I don't know, something like that to say, just download this and you get astrometry.jl, fitzfiles.jl, all this type of stuff, and you're kind of like, you know, that's for Python-type people. Sorry to go on so long.
Sure, yeah, I have two comments. One is I think it's important to think about who isn't in this room, but is already a Julia user in the astronomy community, and how do we bring them in and their packages into our ecosystem together. And the second thing I want to point out is something that you kind of touched on with the VLBI and with the things that I've been talking about with Apogee. I mean, I think we sort of converted a lot of Sloan to at least using Julia data products, and maybe you're slowly converting EHT to people using Julia data products. And I think that, you know, a lot of astronomy revolves around projects, big projects. And especially at the early days, if you can get something that works first, people just like glom onto it. We've seen this with J2ST, we've seen this with a lot of different things. SphereX, just starting to put down data. Roman, about to launch. Like, it's possible that a very targeted, intentional Julia campaign to be the first people that interact and interface with SphereX data or with Roman data could be like really successful for our brand if we're like thinking about this as a branding opportunity. And I just want to throw that out there as something to think about, that like a small amount of effort early in these missions could mean that everyone uses spherex.jl. And then they're like, what's that .jl? We better learn about it. So anyway, that's one thought.
Well, I actually think the biggest benefit would be for the radio, since we're strong. We have a good radio community. If we actually organized, we could beat the pants off CASA and everybody else out there. And that people would really have to start thinking about it. I mean, you know, it takes hours to you know, calibrate, you know, VLA data for 1 hour VL a day takes 3 or 4, 5, 6 hours. I mean, we should be doing that in 15, 20 minutes, you know? It's stuff like that. And once you show the results are better, people have to, you take notice, you get noticed.
I have a couple points with this. One, the centralized effort. I actually think that's pretty critical. We got feedback from an NSF proposal. We had good feedback, like it was all excellent or whatever. And when we talked to our program officer said, well, you know, you guys had 3 separate Julia proposals, and each one was different. We weren't competing, but they were like, oh, you have 3 separate Julia proposals. Why are you doing this? You should have one synthesized proposal. I personally am very frustrated with that, but I think it is something with AstroPi. It's just like, AstroPi proposes for this. If we can come together in like these funding cycles, and you know, maybe not everyone gets what they want, but I think just sticking money into it and just being like, as an organization, Julia asked for this because we need to develop this, might be helpful for future things. I think, you know, once you get 1 or 2, there's more momentum to kind of say, oh, we've got money, we need to keep this going, this has already been successful. But I do think we need to like break through that. For the other one, yeah, I think adding a killer feature is, for like a new instrument or whatever, is super critical. I know for myself, the big thing that we've done is the EHT is a mixed polarization interferometer, so we measure both, depending on the telescope, you measure circular and linear polarization, and this was something that I am not aware of any other package can do. And this has been potentially a big deal for the EHT because we can analyze data years in advance. And even if people got a little upset with us for it originally, I think we're getting to a point where they're gonna just have to do it because we are able to do things 3 years before other people. So I think something along those lines where you can walk in with some package and effectively be like, hey, you know, you're sitting on this, you can't analyze it, we can do this in a fraction of the time is a huge selling point because it kind of leaves them no other option.
Thinking of upcoming data opportunities, Gaia DR4 will be the first with individual epoch astrometry. So that might be another place where a well-positioned set of code could make a big impact. Another thought I had is, imagine the first problem is solved. NSF officer says, here's a check. Who do we want to hire to do the work? So traditionally, I've had graduate students who were astronomy who might have taken my class 1 semester in high-performance computing, or 1 programming class in who knows what, C or Python or whatever, that's kind of worthless. And that's all the training they have, and I drop them into, you know, trying to make something modular, reproducible, performant, threaded, and it's a big ask of their time. An alternative is to go with professional software engineers, but they often don't understand any of the astronomy, and so there's kind of there are trade-offs, right? And so maybe the ideal would be to have a blend of both, but maybe thinking about, like, if we were to put it in as an organization, what would we actually want to fund?
Yeah, I think that's great. I think we've actually had, we've worked with some of the Julia developers like Billy Moses and Valentine with the idea being that we would partially steal some like software dev people's time with astronomers, because I agree, you can't just have one. You end up with the exact thing where you have astronomers and, you know, I'm all right, but we're not like, this ain't our job, right? And then the software devs, they're like, they might like the science, but like, it's not what they do either. So I think when we put these together, it is probably good to, and I think this is one of the strengths, is that because we're so familiar with the Julia community, we can find potentially software dev people and steal some of their time, because they also need funding.
This is not a fully formed thought, but like, I guess I'm thinking about like, who do you target in terms of like people in the Astro community? Do you put more effort into incorporating Julia in your classes and getting students learning it early? Maybe that's not even effective, like you said. Maybe they take your class once and then they forget all of it, and then they try to do a project and none of it stuck.
I would actually say
Or
I mean, I teach a high-performance computing class to graduate students. It is not a Julia class. It is that uses Julia. But in the course of it, more than half of the students see a dramatic improvement in the performance of some code they wrote.
Okay.
And then what do? They tell their advisors, like, hey, I sped up this thing by 2 orders of magnitude.
Yeah.
And then their group, they become their local group's Julia person, you know. And then there's kind of like a tree of advocates. And like Anna, you know, is someone who then moves on and joins your group and contributes. And so there's, I think catching people early does, like I don't want to learn another language. If it's kind of one of their first languages, that's when they're starting, it solves that problem. So I do think early education can make a big difference.
I think on that note, I'm thinking about root, as in the CERN root. I remember when I was a part of the Atlas collaboration, during that point in time, people were kind of moving away from C to use more Python in their analyses. And the reason for that was essentially a lot of students got very annoyed with using C with root, and they made a Python version for it, PyRoot, and it started to develop. And because it was just kind of useful, a lot of people ended up using that more, and that kind of caused a transition. I think there could be something kind of similar for Julia. I imagine, I think the thing that I saw at first that really got me very interested into just fully moving everything into Julia was this plotting capability. I know that for a lot of people that was the same for Python, like moving from whatever they were using, maybe R or MATLAB, and then going into Python because of the plotting capabilities. So or C, yeah, exactly. I think there's some low grassroots effort that can be done to incorporate more people into Julia through a medium that way.
Yeah, kind of related to that. I mean, in the the last AAS tutorial that I gave, you know, it's a 2-day tutorial, and we went to, you know, GPU programming, and that was the second day. I should have made that one of the first things I did. And, you know, we got to the point where, you know, okay, this is how you do GPU programming. It takes 3 lines of code. And the guy types it in, and it comes out, and he goes, wow. And it's like, okay, I sold you, you know. And it's like, I should have moved that up to the first day. It's simple stuff like that where people want to get speed out of that. They want to use the GPUs. And once you show them how easy it is, you know, they're sucked in, basically. And if we can also do that with distributed, then that would be great.
Maybe anything from the audience? No? Yeah.
Yeah, this is, so I am the Atlas root people, and we have our own Julia revolution, albeit slowly. I want to go back to a little bit on the funding thing and just try to, I guess, pick your brains here. So, of course, when any even software-oriented project tried to go for fundings, the science offices in the US funding agencies, whatever, they trying to look for science cases. And when something is established, often they could get ongoing monies for maintaining certain things. But if you want to start something new, certainly it cannot just be that we want to do X in Y language, right? So that's not valuable. And the conversation so far has touched upon that, which is, you know, for example, if there's a new project going, maybe if you start having Julia for that mission, that's a way to get a new. But in terms of the physics directions, what are sort of things going on that maybe you can looking for Julia to do something that other packages currently don't do that can make a science case on its own? Yeah, any thoughts on that?
Yeah, I mean, that's a good point. I think we really realized we cannot just ask for money for software. We've got to justify it with a really strong science objective. And we have identified one project in the X-ray community. The current software to do X-ray spectroscopy just does not cut it. It's one reason for developing software in Julia is because we think we can actually answer that problem. And so yeah, hopefully we'll be able to pursue that in the next year or so. But we're going to have to go to private funding to foundations, something like that.
Yeah, I think we've had moderate success going to private and then packaging it as, you know, a lot of these private companies, data center type ones are like, use our compute type of thing, right? So getting on to different cloud platforms and something, and one of our experiences has been, well, if you fund us, we'll do really cool science, and then also we're going to develop a compute backend so that other scientists can use compute center XYZ, and you get to charge them money, and you get to bring a whole bunch of scientists on board to use their compute on your platform. So this has been moderately successful in a funding proposal for that. It depends on the funder specifically, right? But for private, for these big kinds of corporations, this is kind of how we sold it. Was we're going to do really cool science, but we're also going to demonstrate feasibility of just scientists using your machines.
So I want to say why I think this is difficult, at least in my experience. A lot of the gains that at least I've achieved with Julia are like, instead of using a maximum likelihood, you can actually get a full posterior because it's that much faster. Or you can actually marginalize correctly over everything and get a clean catalog that then can do a reconstruction that doesn't look bad, it looks good. These are all statements that I can make as a statistician and an astronomer that are really hard to communicate to a funding panel, because they can be like, oh, well, someone tried that, and like everyone in the community knows that it didn't really work very well, and that like I have the only catalog that does that well. But it's hard to communicate that, one, that it was necessarily Julia that did that. It's just like, oh, I happened to use Julia to do that. And two, that these are sort of gains that look marginal to other people, but that really aren't. And they're just in these subdomain specific knowledges that I think are hard to communicate. That's just a negative.
We talked about compiling a list of packages or tutorials. What about compiling a list of statistics that people can cite in the proposals for the number of lines of code, reproduced to a pipeline reduced from one to another, or the speed up of a little bit of just like collective bragging for each other to like help provide that incentive both so that our presentations can cite more than just, I can point to my group successes, but it's just one project. Maybe I had one good graduate student, right? Versus when you see the aggregate across this, you can appreciate that it really is the superiority of the language that's enabling us to be so successful. And so maybe that's going to be another thing in one of our shared repositories we could start accumulating.
Yeah, powered by Julia.
Yeah.
Yeah, I wish that was the case. My experience is that does not help. The NASA proposal we had last year, we showed it's 3 times faster than the current de facto standard. Someone said, wow, 3 times faster. Sorry, we're not giving you any money.
Yeah.
I guess I'm really thinking of my own experience working with Comrade in the VLBI science case, that like Julia, the optimization from Julia, like the fact that it's so much faster, the talk that I didn't give. So that science project is literally, it is possible without Julia, but it would be on non-grad student timescale possible. Like it would take just ridiculous, like a ridiculous long time to compute the kind of work that I'm doing now that is like actually being able to be done on a reasonable grad student graduation timescale, and to actually be able to do scientific analysis that, like, if you compare it to the already established algorithms like Clean, it's so much better. And that this technique has been enabled by Julia. So maybe the question is not how much faster is Julia, the question is, these are the science outcomes that have been enabled by Julia because it is fast. Like this, these, like your polarization stuff with Comrade, like that was enabled by Julia. That is a new science result that no one has implemented before that was enabled by Julia. And I think like it has so much science potential, and just being like science enabled by Julia maybe could be a better way to pitch it.
Yeah, so not on the topic of getting like financial resources, but on getting hopefully more mindshare, I would suggest everyone to put in, I don't know, somewhere in the end of the paper, a link to a repo or to a folder where you can just, you have a Julia environment, some like notebooks or scripts to reproduce some or all key parts of the paper, be it figures, plots, and stuff. I just very recently started doing it myself, so like really also a few months ago, but so I don't know of any kind of how it really is perceived and what it changes, but I know that like when I look at the paper and I want like, oh, that's kind of a nice figure, like a nice data set they are using, I just want to do the same, but kind of like switch it to like my set of sources or something. And it's always like difficult, they have all the links like data is here, like algorithm is here, it's like, if I just have a simple notebook or script that I can just tweak a few numbers or like values, rerun it, I'm already kind of like a novice Julia developer.
Yeah, so I have one thing on what Eric said, and I'll just agree that I do that already. I've been doing that for a long time, and it has converted people, specifically undergrads and younger people, who want to reproduce my papers and extend it. It's really helpful if they can just download the Zenodo and then do that. On your comment, like, I mean, I think if you want to know what the SDSS cost is, we know what the cost per spectrum is, we know how many spectra we saved, and we know what the cost per night is. I don't know that they would want us to publish those numbers, though. Like, I think it embarrasses the project to know that, like, that was saved by software. But I mean,
they want funding next cycle.
well, yeah. So I mean, so maybe we could convince them to post that. The other thing that I think is an interesting angle that I've been thinking more about recently is, and maybe it depends on the climate of the administration, but I think you could try to sell this as part of some of the green energy initiatives. Like a lot of astronomy has been talking about not flying to conferences as much. I mean, I think AstroPi has killed more CPU hours in terms of compute and more electricity, than Astro Julia has, and I think that the speedups, if phrased that way as a carbon footprint, could be compelling. And the really question is if people will listen. But I think that's a really compelling direction that I haven't heard people talking about enough, in my opinion.
I just had one question. Don't want to go too long over time, but I'm not in the astronomy community, but I was really fascinated by this. And my question is, maybe if some of the panelists could share why you went out of your way to get into Julia for astronomy, like what the driving factor was, be it the people I work with use it, there's a problem I need to solve, or it's just so much more efficient for the types of things I'm doing. And then maybe if there's some parallels between that, how that might draw more people in.
You mind if I start with that one? So I advocated for Python 30 years ago, okay? I think I kind of hope to think I'm one of the people that got astronomy into Python, okay? And I worked on Python 25 years ago at Space Telescope to develop the infrastructure. And I moved to Julia because it's a better language. I think it's a successor, all right? That's my...
Yeah, so for me, it's not the raw performance, because you can get raw performance in Python. It's just that you can write reasonable code using like structs and whatever like features of the language you use. Like it's composable, you can package it, and then you can use this kind of code, the composable code, and it is fast. In Python, it's very hard to get. It's either fast or nice and convenient.
I think for me, the tagline of reads like Python, runs like C was very accurate for kind of what got me into it. So I started, the first project I worked on was this ray tracing code that I showed. And initially I tried to implement it in Mathematica. And that was not feasible. And then I tried Python. It was a little bit better, but it was, again, not feasible. I noticed that some people had C implementations of the code, but the C implementations aren't, you have dreams of you want it to be automatically differentiable, you want to run on the GPU. It's just like you can't really just take those C implementations and expect it to work. And then I kind of went under this, took this burden of implementing it myself. I was able to implement it really quickly, much more faster than I had anticipated, especially given the amount of lines that exist in the equivalent C code. And not only that, I was able to just write the same algorithm, but just optimize it to be faster than the C codes. I think just the fact that it's so much easier to develop in and get performance out of it was the thing that roped me into it.
I'll be quick. C plus Python. It was I needed something fast, and I didn't want to write reams of C++ code.
This guy. But also right now, that's something that I'm thinking of, especially seeing the interactive plots that Sasha and others have been showing. I think it would be really cool to write interactive papers.
Also mostly who I was working with, Paul and Kazu, one of the other comrade people. And even now, I pretty much use Julia and Python 50-50. I like both of them. I found Julia to be similar, not in performance-wise, but similar in writing it style to Python. And I still am able to use both of them regularly, and I think it's fine, but I would like to use Julia more, and being here has been really helpful for that.
Performance, and I do a lot of distributed computing on HPC, mostly CPU based, and the absolute lack of nonsense trying to go from like 1 core to n cores to n nodes, and this complete simplicity of that in Julia is what sold me.
Yeah, I think similar to Paul, for me it's a C++ alternative, and I think that it's easier to make the case to someone who would have written C++ instead than it is for someone who's coming from Python.
Yeah, I was a convert from C++ back in JuliaCon 3, and started teaching with it with JuliaCon 6. And as an educator, one of the things I love is I can teach a class about data science or high-performance computing where they have to do algorithms and parallel computing, multi-core, distributed GPUs, and I don't need 6 languages, OpenMP and CUDA, and it makes it possible to provide a broad overview of computational science for students in 1 semester because it just eliminates all those distractions. And so I think it's another very valuable tool in education. I think we're going to have to call it a day in terms of the session. Thanks to everybody who came. And once they cut the audio feed, there's a few of us here. If people don't already have a little group they want to go to dinner with or something, I mean, we might make 2 or 3 tables or something, but feel free to come to the front and we can make plans to chat more.